Zeno's dichotomy paradox. Zeno's dichotomy paradox is one of the most intriguing challenges to our common sense understanding of motion, and it has fascinated thinkers for more than 2,000 years. The paradox begins with a seemingly simple observation. To travel from one point to another, you must first cover half the distance, then half of what remains, and then half of the remaining distance again, and so on. At first glance, this endless division suggests that you are never really able to complete the journey because there is always another halfway point to reach. This idea strikes at the heart of how we intuitively understand space, time, and movement. The origins of this paradox lie in ancient Greek philosophy, particularly with Zeno of Elea, who was a student of Parmenides. Parmenides argued that change is an illusion, and that reality is unchanging and indivisible. Zeno devised several paradoxes to support this view, and the dichotomy paradox is among the most famous. By breaking motion into an infinite number of steps, Zeno intended to show that what we perceive as continuous motion is, in fact, impossible if space and time are made up of discrete parts. This radical idea forced ancient thinkers to question the very fabric of reality. To understand the paradox more deeply, consider a simple example. Imagine you want to walk from your front door to a lamp post down the street. According to the logic of the paradox, before you can reach the lamp post, you must first reach the midpoint between your door and the post. Once you've reached that midpoint, you still have the remaining half to cover, and before reaching the end of that half, you again need to cover another halfway segment. This division continues infinitely. The paradox seems to suggest that, since there are an infinite number of these segments, you can never complete your journey because completing an infinite number of tasks would take an infinite amount of time. At the core of this paradox is the concept of infinity. Zeno's reasoning forces us to consider how an infinite number of intervals can sum up to a finite distance. Intuitively, it seems paradoxical that if you add together infinitely many numbers, even if each number is getting smaller, the total could still be finite. The resolution to this puzzle, however, comes from the development of modern mathematics, particularly the ideas surrounding infinite series and calculus. Mathematicians eventually demonstrated that the sum of an infinite series like 1/2 plus 1/4 plus 1/8 plus 1/16 plus does, in fact, converge to 1. This means that while there are infinitely many segments to traverse, the total distance covered is finite. In essence, the infinite series has a limit, a finite sum, which reconciles the paradox with the reality of motion. This mathematical insight, which emerged only in the last few centuries, provided a way to resolve the apparent contradiction posed by Zeno. The introduction of the concept of limits and the rigorous development of calculus by Newton and Leibniz allowed mathematicians to handle infinite processes in a precise manner. Today, we understand that an infinite number of diminishing steps can add up to a finite result, which explains how you can indeed walk from your door to the lamppost despite the infinite subdivisions. This understanding not only dissolves the paradox, but also laid the groundwork for much of modern analysis and the study of continuous change. Beyond its mathematical resolution, Zeno's dichotomy paradox has profound philosophical implications. It challenges us to reconsider our assumptions about the nature of space and time. Are these entities composed of discrete, countable units, or are they continuous, flowing without interruption? The paradox invites a deeper exploration into the structure of the universe. For example, if space were composed of indivisible points, then motion might indeed be impossible because you would never be able to jump from one point to the next without encountering an infinite regress of smaller intervals. However, if space is continuous, then the paradox points us toward a more sophisticated understanding of how finite distances can be constructed from infinitely many parts, a question that continues to be relevant in both philosophy and physics. Historically, Zeno's paradoxes have had a lasting impact on both the fields of philosophy and mathematics. In ancient times, these puzzles forced scholars to grapple with ideas that seemed to defy common experience. The discussions they provoked laid early groundwork for the study of the infinite and the continuous. Over the centuries, as mathematics evolved, Zeno's paradoxes became central to debates about the nature of infinity and the structure of mathematical analysis. They served as a catalyst for the development of methods that could rigorously address infinite processes, ultimately influencing how scientists and philosophers think about change and motion. The legacy of Zeno's dichotomy paradox extends into modern times as well. Today, the paradox is often cited as a historical example of how intuitive reasoning can lead to surprising and counterintuitive conclusions. It reminds us that our everyday experiences of the world, such as walking, running, or driving, are underpinned by deep mathematical principles that can seem almost magical in their ability to reconcile the infinite with the finite. In the classroom, educators use the paradox to illustrate the concept of convergence and to explain how modern mathematics deals with problems that involve infinite sequences and limits. It is a perfect example of how an ancient philosophical puzzle can still be incredibly relevant in contemporary scientific and mathematical discourse. Moreover, the paradox continues to inspire debate among philosophers and scientists. Some argue that it highlights the limitations of human intuition when dealing with abstract concepts like infinity. Others see it as a beautiful demonstration of the power of mathematical reasoning to resolve what initially appear to be insurmountable problems. The discussions that Zeno's paradox has sparked over the centuries serve as a reminder that even simple observations can lead to deep and lasting questions about the nature of reality. As we continue to develop new theories in physics and mathematics, the ideas embodied in Zeno's paradox still encourage us to think critically about how we model the world. In reflecting on Zeno's dichotomy paradox, one is struck by the enduring nature of these ancient questions. Despite the advances in mathematics and science, the paradox continues to captivate our imagination and challenge our understanding. It stands as a testament to the enduring power of philosophical inquiry and the timeless quest to comprehend the infinite. Whether viewed as a clever logical puzzle or as a profound statement about the structure of the universe, Zeno's paradox remains a compelling subject of study, a bridge between the ancient and modern worlds of thought. In conclusion, Zeno's dichotomy paradox is much more than a curious philosophical puzzle. It is a rich source of insight into the nature of infinity, space, and time. The paradox not only challenges our intuitive perceptions of motion, but also paved the way for significant developments in mathematics and philosophy. Through the resolution provided by calculus and the concept of convergent series, we see that an infinite process can indeed yield a finite result, reconciling the seemingly contradictory aspects of motion. Yet, the philosophical questions it raises about the continuity of space and time remain as thought-provoking today as they were in ancient Greece. As we continue to explore and understand the universe, Zeno's paradox serves as a reminder that the simplest questions can often lead to the most profound discoveries. Schrödinger's cat paradox. Schrödinger's cat paradox is one of the most famous thought experiments in modern physics, encapsulating the mysteries and counterintuitive nature of quantum mechanics. Introduced in 1935 by Austrian physicist Erwin Schrödinger, this paradox was designed to challenge the prevailing Copenhagen interpretation of quantum theory and to force us to reconsider the role of observation in determining reality. Imagine a sealed box containing a living cat, a tiny amount of a radioactive substance, a Geiger counter, and a vial of poison. The setup is arranged so that if a single atom of the radioactive substance decays, a random quantum event, the Geiger counter will trigger the release of the poison, killing the cat. According to quantum mechanics, until an observation is made, the atom exists in a superposition of decayed and undecayed states. Consequently, the cat, whose fate is directly tied to the state of the atom, is also in a superposition. It is simultaneously alive and dead. Only when the box is opened and an observation is made does the wave function collapse, and the cat assumes one definite state. This thought experiment forces us to confront the bizarre implications of quantum superposition. In the microscopic realm, particles like electrons or atoms can exist in multiple states at once, a phenomenon that is mathematically described by their wave functions. But when we measure or observe these particles, the act of measurement appears to collapse the wave function, yielding a single definite outcome. Schrödinger's cat takes this idea to the macroscopic level, suggesting that if quantum rules apply universally, then even a familiar object like a cat could exist in two contradictory states at once until it is observed. Schrödinger did not intend for his paradox to be taken as a literal scenario. Rather, it was crafted as a reductio ad absurdum, a way to expose the difficulties inherent in the Copenhagen interpretation of quantum mechanics. This interpretation posits that a quantum system remains in a superposition of states until it is observed, at which point the superposition collapses into one of the possible outcomes. Schrödinger found this notion deeply troubling when applied to everyday objects. After all, in our classical experience, a cat is either alive or dead. It cannot be both simultaneously. The paradox raises profound questions. What constitutes a measurement? Does the consciousness of the observer play a critical role? And where exactly is the boundary between the quantum and classical worlds? Over the decades, numerous interpretations of quantum mechanics have emerged in an attempt to resolve these questions. One of the most intriguing is the many worlds interpretation. According to this view, every possible outcome of a quantum event actually occurs, but in separate branching universes. In the case of Schrödinger's cat, one universe would contain a living cat, while another would contain a dead cat. This interpretation eliminates the need for a wave function collapse, instead suggesting that the universe continually splits into multiple, non-communicating branches. However, this idea brings its own set of philosophical and practical challenges, particularly concerning the nature of reality and the very definition of observation. Despite the theoretical nature of the debate, the impact of Schrödinger's cat extends far beyond academic philosophy. The paradox has become a cultural icon, a symbol for the enigmatic and often non-intuitive realm of quantum mechanics. It challenges our classical understanding of nature and invites us to think deeply about the limits of human perception and knowledge. In classrooms and public lectures, the image of the cat in its dual state is used to illustrate the fundamental mysteries of quantum theory, captivating audiences and inspiring curiosity about the unseen workings of the universe. From a scientific standpoint, the discussions sparked by Schrödinger's cat have paved the way for significant advances in both theoretical and experimental physics. Research into quantum superposition, entanglement, and decoherence, the process by which quantum systems interact with their environment and lose their quantum behavior, has deepened our understanding of how classical reality emerges from quantum laws. In the laboratory, experiments with superconducting circuits, photons, and even large molecules have demonstrated quantum behavior in systems that inch closer to the macroscopic scale, gradually bridging the gap between the quantum and classical worlds. Moreover, the paradox has practical implications in the burgeoning field of quantum technology. Quantum computers, for example, leverage the principles of superposition and entanglement to process information in ways that far surpass the capabilities of classical computers. Quantum cryptography uses the inherent unpredictability of quantum states to create secure communication channels. In these and many other applications, the counterintuitive properties highlighted by Schrödinger's cat are not just theoretical curiosities, but the very foundations upon which new technologies are built. Philosophically, Schrödinger's cat forces us to re-examine the nature of reality itself. It raises questions about determinism, the role of the observer, and the limits of human knowledge. Are the seemingly paradoxical outcomes of quantum experiments reflective of an underlying reality that is fundamentally probabilistic, or do they point to a deeper, hidden order that our current theories are yet to uncover? These questions continue to stimulate debate among physicists, philosophers, and even theologians, contributing to an ongoing dialogue about the meaning of existence and our place in the universe. As we reflect on Schrödinger's cat, it becomes clear that the thought experiment is much more than a playful paradox. It is a profound inquiry into the nature of observation and the fabric of reality, a challenge to our most basic assumptions about the world around us. The paradox compels us to embrace a level of uncertainty and to acknowledge that our classical intuitions might not be sufficient to understand the true nature of the quantum realm. In conclusion, Schrödinger's cat paradox remains a central and enduring puzzle in modern physics, symbolizing the fascinating and sometimes bewildering intersection of quantum mechanics and philosophy. It reminds us that the universe is far more complex than it appears, and that the act of observation can fundamentally alter the reality we experience. Whether you view the paradox as a challenge to the Copenhagen interpretation, an invitation to consider the many-world scenario, or simply as a mind-bending riddle, it continues to inspire both scientific inquiry and philosophical reflection. As we push the boundaries of knowledge with quantum technologies and delve deeper into the mysteries of the cosmos, the legacy of Schrödinger's thought experiment endures, inviting us to constantly question, explore, and redefine our understanding of reality. Thank you for joining me on this exploration of Schrödinger's cat paradox. I hope this discussion has provided you with a deeper appreciation for the profound challenges and exciting possibilities that quantum mechanics presents. The Bootstrap Paradox, Time Travel. The Bootstrap Paradox is a captivating and intellectually challenging concept in the realm of time travel that raises fundamental questions about causality, origin, and the nature of time itself. At its core, the paradox involves a situation where an object, information, or even a person is sent back in time and becomes ensnared in a loop in which its existence is self-contained, with no clear point of origin. Imagine a scenario where a time traveler receives a crucial piece of information, perhaps a scientific theory or a cherished artifact, and then, after using it to achieve a breakthrough, sends that same piece of information back in time to inspire their younger self. This creates a causal loop where the information seems to exist without ever having been created, challenging our everyday understanding of cause and effect. In conventional thought, every effect should have a cause, and every creation should have an origin. However, the Bootstrap paradox defies these expectations by suggesting that something can be both the result and the cause of itself. This idea has fascinated not only scientists and philosophers, but also storytellers and filmmakers who have woven such scenarios into narratives that explore the profound implications of time travel. Numerous science fiction works have presented variations of this paradox, using it as a plot device to question whether destiny is predetermined or if free will can alter a timeline that already seems self-constructed. The concept forces us to confront the possibility that if time travel were possible, the linear progression of time might be replaced by intricate loops where events continuously reinforce one another without a discernible beginning. One of the leading theoretical approaches to resolving such paradoxes is the Novikov self-consistency principle, which posits that any actions taken by a time traveler must be consistent with the timeline they originate from, thus preventing paradoxes from occurring. Under this principle, the paradoxical scenario is resolved not by eliminating the causal loop, but by ensuring that all events, including those that seem to arise without origin, are integrated into a self-consistent history. In this framework, the Bootstrap paradox does not lead to a logical contradiction. Instead, it becomes a manifestation of a universe in which the past, present, and future are intertwined in a way that defies our conventional linear experience of time. Yet, the notion of a self-existing object or piece of information can be unsettling because it challenges the very concept of creativity and originality. When we consider the Bootstrap paradox, we must ask, if an invention or idea is passed through time without ever being truly created, does it diminish the value of human ingenuity, or does it instead hint at a mysterious, underlying structure to the cosmos that we are only beginning to understand? This line of inquiry also intersects with discussions about the nature of identity and memory. If a time traveler carries with them elements of their future self, they might inadvertently alter the sequence of events that led to their original journey, thereby creating a loop where the origins of both their identity and their actions are obscured. The paradox serves as a potent reminder of the limitations of our current scientific paradigms when faced with the concept of time travel. While theories such as general relativity provide a robust framework for understanding the fabric of space-time, they also predict the existence of solutions, like closed time-like curves, that mathematically permit time travel. Yet, these solutions often lead to perplexing scenarios like the Bootstrap paradox, forcing scientists to consider whether our universe inherently prohibits such causal loops through mechanisms that are not yet fully understood. Another perspective is offered by the many worlds interpretation of quantum mechanics, which suggests that every action branches off into different realities. In this view, a Bootstrap paradox might be resolved by positing that the time travel event creates an alternate timeline, thereby sidestepping the issue of a single, uncaused object looping through time. However, this interpretation raises its own set of philosophical and scientific questions about the nature of reality, the possibility of multiple coexisting timelines, and the true meaning of cause and effect in a universe that may be far more complex than our everyday experiences imply. The paradox also invites us to reflect on the inherent circularity present in many human stories and myths. Many legends and historical narratives contain elements of circular causality, stories that seem to have no beginning or end, and the Bootstrap paradox can be seen as a scientific echo of these age-old mysteries. Whether it is a hero receiving a mysterious sword that later becomes the very artifact that inspires their quest, or a wise figure imparting knowledge that ensures their own rise to power, such narratives capture the imagination by suggesting that time itself might be as fluid and enigmatic as the stories we tell. In contemplating the Bootstrap paradox, one is led to consider that time may not be a straightforward progression from past to present to future, but rather a complex tapestry in which all moments are interwoven in a way that challenges our understanding of linearity. This invites a broader philosophical exploration of determinism versus free will, and whether the future is as fixed as the past or if it remains open to change. If time travel were possible, the paradox implies that some events might be predestined to occur, not because of an external force, but as a necessary consequence of the loop itself. Such a scenario raises profound questions about the nature of human agency and the degree to which our actions are truly free. Firmly rooted in both theoretical physics and abstract philosophy, the Bootstrap paradox has practical implications for our understanding of causality and the fundamental laws that govern the universe. It challenges the notion that every event has a clear, traceable lineage and suggests that, under certain circumstances, the origins of events might be shrouded in mystery. The paradox remains a fertile ground for speculation and debate, resonating with our deepest intuitions about time, existence, and the interconnectedness of all things. As our exploration of time travel continues, whether through scientific inquiry, thought experiments, or imaginative storytelling, the Bootstrap paradox stands as a compelling reminder that the nature of time may be far more intricate and surprising than we have ever imagined. Olbers paradox. Olbers paradox begins with a simple yet perplexing question. If the universe is infinite and filled uniformly with countless stars, why does the night sky remain dark instead of being lit up like the surface of a star in every direction? This question puzzled astronomers and philosophers for centuries and has led to a deeper exploration of the nature of our cosmos. Early thinkers assumed that with an endless expanse and an infinite number of luminous bodies, every line of sight should eventually hit a star, rendering the entire sky bright. Yet, when we gaze upward on a clear night, we are met with vast stretches of darkness, a stark contrast that invites us to reconsider our assumptions about the universe. Historically, the paradox was discussed by great minds long before the modern era of astrophysics. Even during the time of Kepler and Halley, there was recognition of the apparent contradiction between an infinite universe and the observable darkness of the night. Heinrich Olbers later formalized the paradox in the 19th century, challenging the notion of an eternal, static universe by highlighting the implications of an unchanging, star-filled cosmos. The expectation was that in a truly infinite and timeless universe, every direction would eventually end on a star, filling the sky with light and leaving no room for darkness. This discrepancy forced scientists to look more closely at the underlying assumptions of cosmic models. A critical breakthrough in understanding the paradox came with the recognition that the universe is not infinitely old. Modern cosmology, built upon the Big Bang Theory, informs us that the universe has a finite age of approximately 13.8 billion years. Because light travels at a finite speed, there exists a limit to the observable universe, meaning that many stars and galaxies are so distant that their light has not had enough time to reach us. This concept of a cosmic horizon explains why the night sky is not uniformly bright. We can only see the light from objects within a certain distance, leaving vast regions of space effectively dark because their light is still en route. Adding another layer to the explanation, the universe is expanding. As space itself stretches, the light emitted from distant galaxies undergoes a redshift, a shift to longer, less energetic wavelengths. In many cases, this redshift moves the light out of the visible spectrum entirely, so even if light from distant stars reaches us, it may not be detectable by the human eye. This cosmic expansion not only limits the distance from which we can receive light, but also dilutes the energy of that light, ensuring that even a universe filled with luminous bodies appears dim when observed from Earth. Moreover, the evolution of stars and galaxies plays an essential role in resolving the paradox. Stars have finite lifespans. They are born, shine for millions or billions of years, and then exhaust their fuel, sometimes ending in supernova or fading into white dwarfs. The rate at which stars form and die has varied over the history of the universe, and this dynamic process means that the density and brightness of stars are not constant across cosmic time. In regions where star formation has slowed or ceased, the accumulated light is less than what would be expected in a universe that is both unchanging and eternal. The remnants of these processes, such as the cosmic microwave background radiation, serve as relics of an early, hotter universe. Yet they do not contribute to a bright night sky in the same way as visible starlight would. Another factor that contributes to the darkness of the night sky is the presence of cosmic dust and gas. Over astronomical distances, light can be absorbed or scattered by interstellar and intergalactic matter. Although this absorption cannot account for the entirety of the dark sky, since any absorbed energy would eventually be re-emitted, it does help to diminish the intensity of light from extremely distant sources. In a universe with a continuous and dense distribution of material, such absorption might initially seem like a viable solution. However, it is the combination of finite age, expansion, and the evolution of stars that truly accounts for the observed darkness, rather than any one factor in isolation. The implications of Olbers' paradox extend far beyond a simple question about light. It touches on fundamental concepts in cosmology, such as the nature of infinity, the passage of time, and the structure of space. The paradox challenges our intuitive understanding by forcing us to confront the limits of observational astronomy and to reconsider the very fabric of the universe. It also illustrates how initial expectations based on everyday experiences can be dramatically overturned by the complex and often counterintuitive realities of cosmic physics. This interplay between what we see and what we theorize has driven astronomers to develop more sophisticated models of the universe, models that integrate the finite speed of light, cosmic expansion, and the dynamic history of star formation. Philosophically, Olbers' paradox invites us to reflect on our place in the cosmos. The dark night sky, once thought to be a void, is in fact a canvas that tells the story of a universe with a beginning, a universe that is continually evolving. It reminds us that our intuitive sense of an endless, unchanging cosmos is challenged by the realities revealed through scientific inquiry. The paradox also raises broader questions about the nature of evidence and the limits of human perception. How much can our senses reveal about a universe that operates on scales of time and space far beyond our everyday experience? In answering these questions, scientists have not only deepened our understanding of cosmic history, but also expanded the philosophical boundaries of what it means to observe and comprehend the universe. In contemplating Olbers's paradox, one appreciates that the darkness of the night sky is not an absence of phenomena, but rather a reflection of the universe's rich and dynamic history. The interplay of cosmic time, the finite speed of light, and the relentless expansion of space collectively ensures that we are privy only to a fraction of the universe's full luminosity. What appears as a quiet, dark expanse is in reality a silent chronicle of stellar births, explosive deaths, and the gradual unfolding of cosmic time, a narrative that continues to evolve as we refine our observational techniques and theoretical models. Ultimately, Olbers' paradox has become a foundational concept in modern cosmology. It serves as a striking example of how questioning a seemingly straightforward observation, the darkness of the night sky, can lead to profound insights about the universe. Far from being a mere curiosity, the paradox underscores the importance of integrating observations with theoretical frameworks. It has propelled scientific advancement by challenging researchers to develop models that accommodate the complexities of cosmic evolution, a journey that has led to the modern understanding of a dynamic, expanding universe born from the Big Bang. As we continue to probe the depths of space with ever more sophisticated instruments, Olbers' paradox remains a powerful reminder of the delicate balance between what is seen and what lies hidden beyond our current observational reach. The dark canvas above us is not an emptiness, but a gateway to understanding the finite nature of our universe, a universe where light, time, and space are intricately interwoven into a narrative that is still unfolding. In pondering the paradox, we are invited to explore not only the physical properties of the cosmos, but also the deeper questions about our own existence within this vast and mysterious expanse. Russell's paradox. Russell's paradox is one of the most profound and far-reaching discoveries in modern mathematical logic, arising from a simple yet startling observation about sets and self-reference. It begins with the idea of forming a set by collecting all sets that do not contain themselves. At first glance, this construction seems innocuous. After all, why not collect together every set that isn't a member of itself? However, the paradox emerges when we ask the critical question, does this set contain itself? If it does, then by its very definition it should not. If it does not, then it must include itself. This self-referential loop creates an inescapable contradiction, undermining the basic assumptions about how sets should behave. The origins of Russell's paradox can be traced back to a period when mathematicians were seeking a solid foundation for all of mathematics by embracing naive set theory. In this framework, any coherent condition was assumed to determine a set, with little thought given to potential pitfalls. Bertrand Russell discovered that this unrestricted approach could lead to logical inconsistencies. His observation revealed that if one is allowed to form any set based on a property, then the set of all sets that do not contain themselves inevitably produces a contradiction. This realization sent shockwaves through the mathematical community in the early 20th century, forcing a re-examination of the very principles upon which mathematics was built. The paradox highlights a deep-seated problem with self-reference. To understand why, imagine trying to define an entity in terms of itself. In our everyday language, self-referential definitions can be confusing, but in mathematics, they must be handled with rigorous precision. Russell's paradox demonstrates that without careful restrictions, self-reference can lead to scenarios where a definition simultaneously demands and denies its own fulfillment. The sheer simplicity of the paradox, arising from such an elementary idea as set membership, has made it a touchstone for debates about the limits of formal systems and the potential hazards inherent in unrestricted abstraction. Historically, the emergence of Russell's paradox was a pivotal moment that spurred the development of more robust axiomatic systems. Mathematicians such as Ernst Zermelo and Abraham Fraenkel, among others, responded to the paradox by devising what is now known as Zermelo-Fraenkel set theory, ZF. In this system, the formation of sets is carefully controlled by specific axioms that prevent the kind of unbridled self-reference that leads to contradiction. By restricting the kinds of properties that can be used to form sets, ZF set theory manages to sidestep Russell's paradox entirely, providing a more secure foundation for mathematics. This work, along with the later introduction of the axiom of choice, resulting in ZFC, has become the standard framework within which most modern mathematical reasoning is conducted. Another influential approach to resolving the issues raised by Russell's paradox was the development of type theory. Type theory introduces a hierarchy of types or levels, ensuring that objects of a certain type can only refer to objects of a lower type, thus avoiding circular definitions. In this view, a set is assigned a specific type, and any set that contains elements must consist of objects of a lower type. Such a stratification prevents the problematic scenario of a set containing itself, as the rules of the system simply do not allow for that possibility. While type theory adds complexity to the foundations of mathematics, it provides a clear and elegant solution to the self-referential issues highlighted by Russell's discovery. Beyond its technical implications, Russell's paradox has had a lasting impact on philosophical thought, particularly in discussions of language, logic, and the nature of truth. The paradox serves as a stark reminder that our intuitions about collections and definitions can sometimes lead us astray when formalized without due care. It challenges the notion that every concept that can be clearly defined corresponds to a well-behaved mathematical object. This insight has encouraged philosophers to adopt a more skeptical stance toward grand theories that claim to encapsulate all of reality within a single, self-contained system. The paradox has, in many ways, foreshadowed later discoveries in logic and philosophy that deal with self-reference and the limits of formal languages. A popular analogy used to illustrate the essence of Russell's paradox is the barber paradox. Imagine a town with a barber who shaves all and only those men who do not shave themselves. The burning question then is, does the barber shave himself? If he does, then by his own rule he should not. If he does not, then he must shave himself. This seemingly simple scenario encapsulates the same logical dilemma as Russell's original set, providing an accessible way to grasp the counterintuitive of self-reference. Through this analogy, one can appreciate how a simple rule, when applied without proper constraints, spirals into a contradiction that defies common sense. The implications of Russell's paradox extend well beyond pure mathematics. In computer science, for example, issues of self-reference and recursion are central to the design of programming languages and the analysis of algorithms. Recursive functions and data structures must be carefully defined to avoid infinite loops or undefined behavior, echoing the need for precision that Russell's discovery highlighted. The paradox has also influenced fields like linguistics and cognitive science, where questions about self-reference, meaning, and interpretation continue to be explored. In each case, the challenge remains the same: how to harness the power of abstraction and self-reference without falling into the traps of contradiction. In the broader context of intellectual history, Russell's paradox stands as a testament to the importance of critical examination of fundamental concepts. It teaches us that even the most seemingly straightforward ideas, like the notion of a set, can harbor hidden complexities that undermine their utility if left unchecked. The paradox forced mathematicians, logicians, and philosophers alike to reconsider the assumptions underlying their theories and to develop more sophisticated methods for constructing and analyzing formal systems. This legacy is evident in the continued evolution of foundational studies, where the lessons learned from Russell's paradox guide current research in logic, mathematics, and even quantum theory. Ultimately, Russell's paradox is much more than a technical anomaly confined to the realm of set theory. It is a powerful illustration of the delicate balance required when defining the building blocks of logic and mathematics. By exposing the vulnerabilities inherent in naive set theory, the paradox has driven decades of research aimed at establishing a more secure and coherent framework for mathematical thought. Its influence reaches into the philosophy of language, computer science, and even the way we understand the limits of human knowledge. In grappling with the paradox, we are reminded that the pursuit of absolute clarity in our theories is both a challenging and essential part of the intellectual journey. Through its enduring influence, Russell's paradox continues to inspire new generations of thinkers. It challenges us to confront the boundaries of our understanding and to remain vigilant against the pitfalls of unexamined assumptions. The paradox not only reshaped the landscape of mathematical logic, but also left an indelible mark on the broader quest for knowledge. In this sense, it serves as a lasting reminder that the tools we use to understand the world must be as carefully constructed as the phenomena they aim to explain. The twin paradox. The twin paradox is one of the most famous thought experiments in the theory of relativity, illustrating in a striking and counterintuitive way how time can behave differently under varying circumstances. Imagine two twins. One stays on Earth while the other embarks on a journey through space at speeds close to the speed of light. According to Einstein's theory of special relativity, time passes at different rates for observers in relative motion, a phenomenon known as time dilation. For the traveling twin, the high velocity means that time essentially slows down compared to the twin who remains on Earth. When the spacefaring twin returns home, they are younger than their sibling. At first glance, this outcome appears paradoxical, because from the traveling twin's point of view, it might seem that the earthbound twin was the one moving away and then coming back. This reciprocal perspective raises the puzzling question: how can each twin see the other's clock running slower, yet only one ends up aging less? The apparent contradiction arises because, in special relativity, motion is relative. If two observers move inertially, that is, without acceleration, each can consider themselves at rest and the other in motion, so each would indeed see the other's clock ticking more slowly. However, the twin paradox is not a true contradiction because the two twins do not share equivalent conditions throughout the experiment. The traveling twin must accelerate to turn around and return to Earth, while the earthbound twin remains in an inertial frame throughout the journey. This acceleration breaks the symmetry between the twins' experiences. In the framework of special relativity, inertial frames are equivalent, but non-inertial frames, those involving acceleration, are not. Thus, the traveling twins experience is fundamentally different, and this difference in the world lines of the two twins resolves the paradox. To explore this further, it is useful to consider the mathematics of time dilation. In special relativity, the time experienced by a moving clock is related to the time in a stationary frame by the Lorentz factor, denoted by gamma. This factor is defined as gamma equals 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the moving observer and c is the speed of light. When v is a significant fraction of c, gamma becomes much larger than 1, meaning that the moving twins clock ticks considerably slower compared to the earthbound twins clock. This mathematical relationship quantifies the effect of time dilation and provides a precise explanation for why the traveling twin ages less over the course of their journey. It is important to note that these calculations assume ideal conditions and instantaneous changes in velocity for simplicity. But even when the effects of gradual acceleration are taken into account, the essential conclusion remains the same. A key element in resolving the twin paradox lies in the distinction between inertial and non-inertial frames of reference. In an inertial frame, objects move at constant velocity, and the laws of physics take on their simplest form. The earthbound twin remains in an essentially inertial frame, experiencing a consistent passage of time. The traveling twin, on the other hand, must undergo acceleration when departing, turning around, and decelerating upon return. These periods of acceleration are crucial because they signal a departure from the symmetrical conditions that would allow for mutual time dilation. In the context of general relativity, acceleration and gravity are intimately connected, a principle encapsulated in Einstein's equivalence principle. Even though the twin paradox is usually discussed within the framework of special relativity, acknowledging the role of acceleration enriches our understanding of how and why time is experienced differently by the two twins. Experimental evidence has supported the predictions of time dilation that underpin the twin paradox. For instance, precise measurements using atomic clocks have shown that clocks on high-speed aircraft or satellites tick at slightly different rates compared to those on Earth. The famous Hempel experiment conducted in the 1970s involved flying atomic clocks around the world and comparing their time to clocks that remained on the ground. The results were in close agreement with the predictions of relativity, lending empirical support to the idea that time is not absolute, but is relative to the observer's motion. Similarly, particles moving at high speeds in accelerators exhibit extended lifetimes compared to when they are at rest, a phenomenon that can be directly attributed to time dilation. The twin paradox also serves as a gateway to deeper philosophical questions about the nature of time and our understanding of reality. In our everyday experience, time appears to flow uniformly and inexorably forward, a perception that seems at odds with the flexible, relative nature of time revealed by relativity. The paradox challenges the notion of absolute time and forces us to reconsider how time is intertwined with space and motion. It compels us to ask whether time is an independent backdrop against which events occur, or whether it is a dynamic quantity that is affected by the very processes that occur within the universe. These questions have profound implications not only for physics, but also for philosophy and our broader conception of reality. The implications of the twin paradox extend beyond the realm of theoretical physics. It has influenced our understanding of how the universe operates on the most fundamental level, reshaping our ideas about space, time, and causality. The thought experiment underscores the importance of considering the role of the observer in the measurement of time and highlights that the passage of time can vary depending on the observer's frame of reference. This realization has paved the way for advances in fields ranging from cosmology to quantum mechanics, where the interplay between time and observation continues to be a topic of intense investigation. The twin paradox remains a powerful demonstration of the non-intuitive and elegant structure of the physical laws that govern our universe. At its core, the twin paradox is a testament to the revolutionary insights of Einstein's theory of relativity. It shows that our classical intuitions about time and motion do not hold when objects move at speeds approaching that of light. Instead, time becomes a malleable quantity, stretching and contracting depending on the relative motion of observers. This leads to situations where two individuals, starting from the same point in time and space, can experience vastly different durations of time. The twin paradox, therefore, not only illuminates the peculiar consequences of high-speed travel, but also invites us to explore the fundamental nature of time itself, a subject that continues to captivate physicists and philosophers alike. In summary, the twin paradox encapsulates the counterintuitive predictions of special relativity by presenting a scenario where one twin ages less than the other due to the effects of high-speed travel and acceleration. The paradox is resolved by recognizing that the traveling twin's journey involves non-inertial phases, periods of acceleration that break the symmetry of the situation. Through mathematical formalism and experimental verification, time dilation has been firmly established as a real and measurable phenomenon. Far from being a logical contradiction, the twin paradox serves as a profound illustration of how time, far from being absolute, is deeply intertwined with motion and the structure of space-time. It challenges our conventional understanding of time and remains one of the most engaging and enlightening thought experiments in modern physics. The Fermi Paradox. The Fermi Paradox is one of the most provocative and enduring questions in our quest to understand our place in the cosmos. It arises from a simple yet perplexing observation. Given the vast number of stars in the Milky Way, and the even greater number of galaxies in the universe, it seems statistically likely that intelligent life should have arisen many times over. Yet, despite decades of searching, we have found no definitive evidence of extraterrestrial civilizations. This apparent contradiction between the high probability of alien life and the stark silence of the skies forms the essence of the Fermi Paradox. The paradox is often summarized by the question, "Where is everybody?" This question, posed by physicist Enrico Fermi in the mid-20th century, challenges us to reconcile our understanding of the universe with the absence of clear signs of other intelligent beings. On one hand, the Milky Way alone contains hundreds of billions of stars, many of which are similar to our Sun, and a significant fraction of those stars are likely to host planets in their habitable zones. On the other hand, despite these promising prospects, our searches, whether through radio signals, optical observations, or other methods, have not yielded any incontrovertible proof that we are not alone. Several explanations have been proposed to resolve the Fermi paradox, each attempting to fill the gap between expectation and observation. One possibility is that intelligent life is exceedingly rare, emerging only under a unique set of circumstances that are seldom replicated in the universe. This idea is sometimes encapsulated in the rare Earth hypothesis, which argues that while microbial life might be common, the evolution of complex technological organisms may require a series of fortuitous events and conditions that are extraordinarily uncommon. If Earth is indeed a rare oasis of life in a vast desert, then the silence we observe is simply a reflection of the scarcity of civilizations capable of interstellar or travel. Another intriguing possibility is that while intelligent civilizations might be relatively common, they are either too short-lived or too self-destructive to leave a lasting mark on the cosmos. This notion is often tied to the idea of the Great Filter, a critical threshold or series of challenges that life must overcome to reach a stage of advanced, sustainable civilization. If the Great Filter lies ahead of us, it might suggest that many civilizations self-destruct through war, environmental collapse, or technological mishaps before they can expand into the stars. Conversely, if the filter is behind us, then it may have been an extremely improbable step in our own evolution that we fortunately managed to surpass. A further class of explanations centers on the possibility that extraterrestrial civilizations might choose to remain hidden or operate in ways that make them undetectable to us. For instance, the zoo hypothesis suggests that advanced civilizations are aware of our existence, but have deliberately refrained from contacting us, perhaps to allow our natural evolution and societal development to proceed without interference. Similarly, there is the idea that alien societies might use communication methods or technologies that are so different from our own that our current instruments and methods simply do not register their signals. In this scenario, the silence is not a sign of absence, but rather of a profound difference in modes of existence and communication. Some theorists have even entertained more radical notions, such as the idea that we are living in a simulation, or that our perception of reality is so limited that we are unable to grasp the true nature of interstellar communication. From this perspective, the Fermi Paradox becomes not just a question of physical detection, but a deeper inquiry into the nature of consciousness, reality, and the limits of human understanding. The search for extraterrestrial life thus becomes intertwined with fundamental questions about what it means to be intelligent and how we interpret the signals we receive from the universe. The implications of the Fermi Paradox extend far beyond astronomy and astrophysics. They challenge our assumptions about the inevitability of progress, the universality of technological advancement, and even the destiny of human civilization. If intelligent life is indeed a rare phenomenon, then our own existence takes on an added significance, a reminder of the delicate balance of conditions that have allowed life to flourish on Earth. On the other hand, if the silence we observe is due to self-destruction or deliberate isolation by advanced societies, it serves as a sobering warning about the potential pitfalls of unchecked technological growth and the importance of developing a sustainable path for our own future. This paradox has also spurred a great deal of scientific and philosophical inquiry, inspiring researchers to develop new ways of searching for life beyond Earth. Projects such as the Search for Extraterrestrial Intelligence, SETI, have dedicated significant resources to scanning the skies for radio signals that might indicate the presence of distant civilizations. Advances in telescope technology, such as the launch of space-based observatories and the development of powerful ground-based arrays, continue to push the boundaries of what we can observe, offering hope that we may eventually detect even the faintest whispers from another world. Yet, the Fermi Paradox remains unresolved, serving as a profound reminder of the mysteries that still lie at the heart of our cosmic exploration. Whether the answer lies in the rarity of life, the brevity of technological civilizations, or the limitations of our current methods, the paradox challenges us to think critically about the assumptions we make regarding life in the universe. It forces us to confront the possibility that our understanding of the cosmos might be incomplete or even fundamentally flawed. In contemplating the Fermi Paradox, we are invited to reflect not only on the vastness of the universe, but also on the depth of our curiosity and the limits of our knowledge. It compels us to ask questions about the nature of life, intelligence, and communication on a scale that stretches our imagination and our scientific capabilities. The paradox stands as a testament to both the power and the humility of human inquiry, an acknowledgement that even as we reach for the stars, the answers we seek may be more elusive and complex than we ever anticipated. Ultimately, the Fermi Paradox is more than just a scientific puzzle. It is a mirror reflecting our hopes, fears, and aspirations as a species. It encapsulates our desire to understand whether we are alone in the universe, while also reminding us of the profound responsibilities that come with our existence. As we continue to search the cosmos and refine our technologies, the paradox remains a beacon of mystery, a challenge to push the boundaries of our knowledge and to embrace the unknown with both scientific rigor and imaginative wonder. The Friendship Paradox. The Friendship Paradox is a counterintuitive observation about social networks that reveals how, on average, most people have fewer friends than their friends do, a phenomenon that arises from the inherent biases in network structure and sampling. At its core, the paradox is based on the idea that individuals who are more socially connected are more likely to appear in the friend lists of others, thereby skewing the overall average upward. When we examine a social network as a collection of nodes, individuals, connected by edges, friendships, the average degree, the number of friends per person, is calculated by summing the degrees of all individuals and dividing by the total number of individuals. However, when one samples a friend at random, the likelihood of picking a person with a high degree is proportional to the number of friends they have, meaning that these well-connected individuals are overrepresented in any random sample of friends. First identified and popularized by sociologist Scott Feld in 1991, the friendship paradox has since been observed across various social networks, from small communities to vast online platforms, and it has far-reaching implications not only in sociology, but also in psychology, epidemiology, and even marketing. For example, in the context of public health, understanding this paradox is crucial for designing effective vaccination strategies. Since highly connected individuals are more likely to spread diseases, targeting them, or even targeting the friends of randomly selected individuals, can be a more efficient method of immunization than random vaccination, as these strategies exploit the same sampling bias that underlies the friendship paradox. Beyond its applications in health, the paradox also affects how we perceive social status and popularity. Many people, upon noticing that their friends seem to have larger social circles, might feel that they are less popular, even though their own number of connections might actually be typical for the network. This social comparison can have profound psychological effects, leading to feelings of inadequacy or a distorted, especially in an era where social media platforms amplify these perceptions by highlighting the expansive networks of influencers and celebrities. On social media platforms such as Facebook, Twitter, and Instagram, users often observe that the individuals they interact with, whether by liking, sharing, or commenting, appear to have significantly more followers or friends, reinforcing the idea that everyone is doing better in terms of social connectivity. This observation is not merely anecdotal. Empirical studies have confirmed that the friendship paradox is a robust statistical property of networks with skewed degree distributions, where a small number of highly connected nodes, often referred to as hubs, exist alongside many nodes with relatively few connections. The presence of these hubs ensures that when a friend is selected at random, the probability of encountering a hub is higher than what one would expect from a uniform distribution of connections. In addition to its social and psychological dimensions, the friendship paradox has sparked interest in the field of network science and has led researchers to explore its generalizations. One such extension is the generalized friendship paradox, which examines how other attributes, such as wealth, happiness, or influence, are distributed among friends compared to the general population. In many cases, it is found that not only do your friends tend to have more friends, but they also tend to exhibit higher levels of these other attributes, although such findings must be interpreted with caution and an understanding of the underlying biases. The paradox also raises important methodological considerations for researchers studying social networks. Surveys and studies that ask individuals about the number of friends they have or about the attributes of their friends can be inadvertently biased by the overrepresentation of highly connected individuals. Researchers must therefore use techniques to correct for this sampling bias in order to obtain accurate representations of the network's true structure. Moreover, the friendship paradox challenges our intuitive notions of what is average or normal within a social context. It forces us to question how our perceptions are shaped by the hidden mathematics of networks, and reminds us that the data we observe on a day-to-day basis can be misleading if not interpreted in the proper context. For instance, while it may seem that everyone else is more popular or more successful, this apparent discrepancy is largely a statistical artifact rather than a reflection of any inherent flaw or deficiency in one's own social network. The implications of the friendship paradox extend into many aspects of everyday life. In workplaces, for example, employees might feel that their colleagues are more well-connected or influential, which can impact morale and job satisfaction. Similarly, in academic and professional settings, the overrepresentation of highly connected individuals in social or professional networks can affect how opportunities and information are disseminated, thereby reinforcing existing hierarchies and inequalities. In the realm of marketing and advertising, companies often leverage the principles behind the friendship paradox by targeting individuals who are more connected or influential within their networks, knowing that these individuals can serve as effective conduits for word-of-mouth promotion and viral marketing campaigns. By understanding the dynamics of the friendship paradox, marketers can design strategies that take advantage of the fact that information tends to spread more rapidly through highly connected individuals, leading to more efficient and impactful campaigns. Additionally, the paradox invites us to reflect on the broader implications of connectivity in our increasingly networked world. As technology continues to reshape the ways in which we interact, the fundamental principles of network science become ever more relevant. The friendship paradox serves as a compelling reminder that the structures underlying our social interactions are not random, but are instead governed by statistical laws that can have surprising and sometimes profound effects on how we perceive ourselves and our place in the world. Whether through its implications for public health, its influence on self-esteem, or its utility in designing more effective social interventions, the friendship paradox offers valuable insights into the nature of human connectivity and the unexpected ways in which our social networks are organized. This phenomenon, deeply rooted in the interplay between individual behavior and collective dynamics, continues to inspire research and discussion among scientists, policymakers, and everyday individuals alike, offering a window into the hidden patterns that shape the fabric of our social lives and reminding us that in the complex world of human relationships, appearances can be deceiving and averages can be remarkably misleading. Simpson's paradox. Simpson's paradox is a fascinating statistical phenomenon that challenges our conventional understanding of data analysis by showing how trends that appear in several distinct groups can be reversed when the data is combined. At its core, the paradox occurs when the relationship between two variables in different subgroups contradicts the relationship observed in the aggregate data. This surprising result is not a flaw in statistical methods, but rather a reflection of how different weights and group sizes can influence overall outcomes, leading to conclusions that may seem counterintuitive at first glance. Imagine a scenario in a clinical trial where two treatments are compared for their effectiveness. In separate analyses of patients with mild and severe forms of a disease, treatment A might outperform treatment B in each subgroup. However, when the data from both groups is combined, the overall results could show that treatment B is more effective than treatment A. This reversal happens because the proportion of patients in each subgroup is not the same. One subgroup might have many more patients than the other, so its results have a greater influence on the aggregate outcome. The key idea here is that the overall effect is a weighted average of the subgroup effects, and if the groups are imbalanced in size or in other important ways, the aggregated data can mask the true performance observed within each individual group. A well-known example of Simpson's paradox can be seen in university admissions data. Consider a university where individual departments report that they admit a higher percentage of female applicants than male applicants. Yet, when all the department's data is combined, the overall admission rate might indicate that women are admitted at a lower rate than men. This apparent contradiction arises because departments vary greatly in both their admission rates and in the number of applicants they receive. Departments with lower admission rates might have received a disproportionately high number of female applications, while departments with higher admission rates could have attracted more male applicants. The aggregate data, therefore, reflects not only the admission rates, but also the varying sizes and competitiveness of each department, resulting in a reversal of the trends seen within each department. The underlying mechanism of Simpson's paradox is intimately tied to the mathematics of weighted averages and the influence of confounding variables. When data is aggregated, the overall average is determined not only by the individual subgroup outcomes, but also by the relative size of each subgroup. If one subgroup, for example, has a significantly larger number of observations, its characteristics will heavily influence the overall statistic. Additionally, if there is a lurking variable, one that is not immediately apparent, that affects the outcome, the aggregated data may show a misleading trend because the impact of this variable is not uniformly distributed across all subgroups. This is why analysts must carefully consider stratification and control for potential confounders to avoid drawing erroneous conclusions from aggregate data. Historically, Simpson's paradox was first formally described in the mid-20th century by Edward H. Simpson, Although the underlying ideas had been recognized earlier by statisticians and researchers in various fields, Simpson's work brought attention to the risks of drawing conclusions based solely on aggregated data, prompting a deeper investigation into how data should be analyzed and interpreted. Over the decades, the paradox has become a standard example in statistics and data science courses, highlighting the importance of looking beyond surface-level statistics and understanding the nuances of subgroup dynamics. Its lessons have been applied across numerous disciplines, including medicine, economics, social sciences, and public policy, demonstrating that the way data is grouped and weighted can have a profound effect on the conclusions we draw. In the realm of medicine, Simpson's paradox has real-world implications that can affect patient outcomes and treatment decisions. Clinical trials often divide patients into subgroups based on factors such as age, severity of illness, or pre-existing conditions. A treatment that appears effective in each of these subgroups might seem less effective, or even harmful, when the results are aggregated if one subgroup disproportionately influences the overall outcome. This situation can lead to misinterpretations that affect treatment guidelines and healthcare policies, underscoring the need for careful analysis that accounts for subgroup differences. By recognizing the potential for Simpson's paradox, researchers and clinicians are encouraged to conduct stratified analyses and use statistical methods that properly account for the structure of the data. The implications of Simpson's paradox extend beyond healthcare. In public policy and economics, aggregated data can sometimes lead to misleading conclusions that affect decision-making. For instance, a government might implement a policy that appears to reduce unemployment when looking at the overall figures, yet a closer examination by region or demographic group might reveal that unemployment has actually increased in certain areas. Such discrepancies highlight the danger of relying solely on aggregate data without considering the underlying subgroup variations. Policymakers must therefore be vigilant in dissecting data to ensure that policies are truly effective for all segments of the population, rather than just appearing beneficial when viewed in the aggregate. From a mathematical perspective, Simpson's paradox serves as a reminder of the importance of understanding conditional probabilities versus marginal probabilities. When data is divided into subgroups, the conditional probability of an event occurring in each subgroup can differ markedly from the overall or marginal probability observed when the groups are combined. This difference is often a result of confounding factors that have not been accounted for in the overall analysis. In essence, Simpson's paradox teaches us that the context in which data is presented matters greatly. The statistical relationships observed in the aggregate may hide complex interactions and dependencies that only become visible when the data is examined in finer detail. In today's data-driven world, where large datasets are routinely analyzed to guide decisions in business, healthcare, and government, the lessons of Simpson's paradox are more relevant than ever. The paradox underscores the importance of critical thinking and methodological rigor in data analysis. It reminds us that data can be interpreted in many ways, and without careful attention to how that data is structured, we risk making decisions based on misleading information. Whether it is designing more effective public health interventions, creating fairer admissions policies, or developing sound economic strategies, understanding and mitigating the effects of Simpson's paradox is essential for drawing accurate and meaningful conclusions. Ultimately, Simpson's paradox is not a statistical anomaly to be dismissed. It is a powerful illustration of the complexity inherent in data analysis. It challenges us to look beyond the apparent simplicity of aggregated data and to engage with the deeper, often hidden dynamics that influence outcomes. By embracing the insights provided by Simpson's paradox, analysts, researchers, and decision-makers are better equipped to navigate the intricacies of modern data, ensuring that the conclusions they reach are robust, reliable, and truly reflective of the underlying reality. This deep dive into Simpson's paradox serves as a valuable reminder of the care and precision required when interpreting data in any field, and it encourages us to continually question and refine our analytical approaches. The Abilene Paradox. The Abilene Paradox is a fascinating social phenomenon that reveals how groups sometimes take actions that no one truly desires, simply because each individual mistakenly assumes that their own objections are unique. It all started when management expert Jerry B. Harvey introduced the concept in 1974 through an anecdote about his own family. On a sweltering Texas afternoon, the family agreed to take a long, uncomfortable drive to Abilene for dinner, even though deep down, none of them actually wanted to make the trip. Each member, not wanting to disrupt what they believed was the group's consensus, chose silence over honesty, and the result was a collective decision that left everyone disappointed. This story perfectly encapsulates the Abilene Paradox, a situation in which the desire to maintain group harmony leads to decisions that contradict everyone's private preferences. At its core, the paradox highlights a breakdown in communication. In many group settings, individuals assume that the absence of objections means full agreement. However, this is often a misinterpretation. People may refrain from speaking up due to fear of conflict or a deep-seated need to be seen as cooperative. Instead of voicing their true opinions, they let the silence of others reinforce the mistaken belief that everyone else is in favor of the proposed plan. The result is a decision that, while seemingly unanimous, is actually the product of widespread dissent that was never expressed. This dynamic is not only relevant in everyday family decisions, but also in larger organizational where the stakes can be much higher. In the workplace, the Abilene Paradox can have significant implications. Imagine a corporate board meeting where a new strategic initiative is proposed. Even if several board members have reservations about its feasibility, they might choose not to voice their concerns because they assume that their colleagues are enthusiastic about the plan. Over time, this leads to decisions that do not reflect the true collective judgment of the group, potentially resulting in wasted resources, missed opportunities, or even major failures. The paradox, therefore, serves as a warning. Decisions made to preserve an illusion of agreement can undermine the very goals the group seeks to achieve. It reminds us that effective decision-making requires not just consensus, but honest and open communication. One of the key reasons behind this paradox is the human desire for social acceptance. We naturally seek to belong, and the fear of isolation or being labeled as a troublemaker can be powerful motivators to keep silent. This action anxiety means that even when individuals recognize that a decision might lead to negative outcomes, they hesitate to challenge the status quo because they worry about the repercussions of dissenting. When everyone is caught in this cycle of self-censorship, the group is left with an appearance of unanimity that is, in fact, misleading. The very environment that values harmony over honesty can quickly spiral into a collective misjudgment, where decisions are based on false assumptions rather than on robust discussion and critical analysis. It is important to differentiate the Abilene Paradox from similar phenomena like groupthink. While both involve a breakdown in genuine dialogue, groupthink usually refers to situations where conformity is enforced by strong group cohesion or dominant personalities, often leading to a suppression of dissent. The Abilene Paradox, on the other hand, occurs when individuals individually choose to go along with a plan because they mistakenly believe their own preferences are in the minority. In groupthink, the pressure is external and often overt. In the Abilene Paradox, the pressure is internal, rooted in the fear of being the odd one out. Both can lead to suboptimal outcomes, but understanding their subtle differences can help leaders design better strategies to foster open and honest communication. To mitigate the risks of the Abilene Paradox, organizations must focus on creating an environment of psychological safety. This means establishing a culture where every team member feels secure enough to voice their opinions, even if they go against the prevailing trend. Practical strategies include appointing a devil's advocate during discussions, which not only encourages different viewpoints, but also signals that dissent is both acceptable and valuable. Another approach is to encourage anonymous feedback or pre-meeting surveys, where individuals can express their true thoughts without the immediate fear of judgment. By ensuring that everyone's perspective is heard, the group can avoid the trap of false consensus and make decisions that genuinely reflect the collective will. The paradox also teaches us an important lesson about the nature of consensus. True consensus is built on an honest assessment of all ideas and concerns, not on a facade of agreement. When people withhold their objections, decisions are made based on incomplete information, often leading to outcomes that are later regretted. In both personal and professional settings, the failure to address dissent can result in decisions that undermine overall satisfaction and effectiveness. Whether it's choosing a restaurant with friends, planning a family vacation, or setting corporate strategy, the willingness to engage in constructive debate and to challenge assumptions is critical. Open dialogue not only improves decision quality, but also strengthens trust among group members, making future collaborations more effective and resilient. Moreover, understanding the Abilene Paradox encourages leaders to reflect on their own behaviors. Often, the burden of creating an open environment falls on those in leadership positions. By modeling transparency and actively seeking out dissenting opinions, leaders can break the cycle of assumed agreement. It's not just about avoiding bad decisions. It's about cultivating a culture where every member feels empowered to contribute their genuine thoughts. This approach not only leads to better decision-making, but also fosters a sense of ownership and engagement among team members as they see that their input truly matters. On a broader level, the Abilene Paradox serves as a cautionary tale for society at large. In a world where social media and digital communications often amplify the appearance of consensus, the risk of falling into similar traps becomes even greater. People may hesitate to express unpopular opinions, believing that the loudest voices represent the majority. This dynamic can stifle innovation, reinforce echo chambers, and ultimately lead to decisions that do not benefit the collective. Whether in public policy, corporate governance, or everyday social interactions, the imperative remains the same: to foster environments where genuine dialogue is encouraged and where true consensus can emerge from the free exchange of ideas. In summary, the Abilene Paradox is a powerful reminder of how our inherent desire for social harmony can sometimes lead us astray. When individuals choose silence over honesty, the resulting decisions may reflect an illusion of agreement rather than the true preferences of the group. By recognizing this paradox and taking deliberate steps to encourage open communication, organizations and individuals alike can avoid the pitfalls of false consensus. In doing so, they can ensure that decisions are not only more reflective of true collective wisdom, but also more effective in achieving their intended goals. This understanding is essential, not just for better management practices, but for building more inclusive, innovative, and resilient communities in every sphere of life. Newcomb's Paradox. Newcomb's paradox is a thought experiment that cuts to the heart of decision theory and free will. Imagine you're faced with two boxes. Box A, which is transparent, clearly contains $1,000, and Box B, which is opaque, either contains $1 million or nothing at all. Before you make your choice, a nearly infallible predictor, someone whose track record for predicting human decisions is astonishingly high, has already determined what you will do. The rules are as follows. If the predictor has foreseen that you will take both boxes, then Box B will be empty. But if it predicts that you will take only Box B, then it will have placed $1 million inside it. Now, you must decide. Do you take both boxes, two boxing, or only the opaque Box B, one boxing? At first glance, the argument for taking both boxes seems compelling. After all, no matter what the predictor did, you will still receive an extra $1,000 by taking Box A. If the predictor already placed $1 million in Box B, taking both boxes gives you a total of $1,001,000. If Box B is empty because the predictor anticipated you'd take both, then you still get $1,000 from Box A. So it appears that two boxing is the dominant strategy. Why not grab the extra cash? But here's where the paradox kicks in. If you believe the predictor is almost always right, then your decision isn't made in a vacuum. The predictor's near-perfect accuracy implies that if you choose only Box B, it's very likely that Box B contains $1 million. In this view, by one boxing, you could walk away with $1 million, while two boxing almost certainly results in a mere $1,000. Two conflicting lines of reasoning. 1. A straightforward causal approach that tells you, take both boxes because you get an extra $1,000 no matter what. And the other, an evidential approach that says, if the predictor is right, then the choice you make is already correlated with what's in Box B, so taking only Box B is the way to maximize your gain. This conflict challenges our intuition about rational decision-making. On one hand, if you use a traditional, causally oriented decision theory, you might reason that the contents of the boxes are already fixed by the time you decide. They don't change based on your current choice. Therefore, taking the additional $1,000 in Box A is a free bonus. On the other hand, if you adopt an evidential or even a kind of timeless decision theory perspective, you acknowledge that your choice is a reflection of the predictor's almost infallible model of you. In this light, choosing only Box B is evidence that the predictor anticipated your rational one boxing and therefore placed the $1 million inside. In effect, your decision seems to cause the outcome in a counterintuitive way, even though the money was already placed before you made your decision. The heart of the paradox is that both lines of reasoning seem logically compelling. Causal decision theory, which looks at the outcomes as fixed after the predictor has made its move, would insist that no matter what, taking both boxes improves your payout by a marginal amount. Evidential decision theory, however, takes into account the statistical correlation between your choice and the predictor's forecast. If you are the type of person who won boxes, then it's highly likely the predictor foresaw that and rewarded you with a full $1 million in Box B. This difference leads to a deep philosophical debate. Should one base a decision on what seems to be causally available, or should one consider the evidence that your decision reveals about the world, even if that evidence is about something already determined? Some have suggested that the paradox forces us to re-examine the very notion of free will. If the predictor is so accurate that your choice seems predetermined, then how can you be said to have free will? Yet if you believe you have free will, then perhaps the predictor's success is not as infallible as claimed, which might tip the balance back in favor of two-boxing. Alternatively, some have argued that the paradox highlights the limitations of classical decision theories, and that newer theories, such as timeless decision theory, offer a more coherent way to understand such dilemmas by allowing for decisions that are acausal in a sense. Critics of the one-boxing argument might say that it commits a kind of fallacy by assuming that your decision somehow influences a fixed past event. After all, the predictor already placed the money in the boxes. Yet the paradox isn't about causation in the usual sense. It's about the correlation between your and the predictor's near-perfect foresight. In a world where the predictor is almost always right, your choice is not an independent act, but is statistically tied to the contents of box B. Even though the money is already there, your decision tells you something about what was placed in the box. This interplay between correlation and causation is what makes Newcomb's paradox so compelling and enduring. The implications of Newcomb's paradox extend far beyond a hypothetical execution of money. It has been used as a touchstone in debates over predictive models in economics, artificial intelligence, and even the philosophy of mind. Some proponents of one-boxing argue that if you adopt a decision theory that rewards the type of reasoning that leads to one-boxing, then you can achieve better outcomes in scenarios where predictive accuracy is high. Others maintain that the intuitive appeal of two-boxing cannot be dismissed because, after all, the extra $1,000 is a free gain if the predictor's choice has already been made. In practical terms, Newcomb's paradox forces us to question how we value our decisions. Should we consider the evidence that our decisions are already predicted by a model of our behavior? And if so, what does that mean for our understanding of rational choice? The paradox doesn't yield a single definitive solution. Rather, it exposes the deep-seated conflicts between different approaches to decision-making. Whether one leans toward one-boxing or two-boxing depends largely on which theoretical framework one finds more convincing: causal decision theory or evidential decision theory. Ultimately, Newcomb's paradox remains a fertile ground for debate because it touches on questions that are at the core of philosophy and economics. It challenges us to reconcile our intuitions about free will with the seemingly deterministic predictions of a superintelligent being. It also forces us to grapple with the idea that sometimes our choices are best understood not in isolation, but as part of a broader web of predictions and correlations that extend into the past. In this way, Newcomb's paradox isn't just an abstract puzzle. It's a window into the complexities of human decision-making, the nature of prediction, and the enduring mystery of what it means to choose freely in a world that might, after all, be more predictable than we'd like to believe. The unexpected hanging paradox. The unexpected hanging paradox is a classic logical puzzle that has puzzled philosophers, mathematicians, and logicians for decades. In its most common form, a judge tells a condemned prisoner that he will be hanged at noon on one weekday in the following week, and that the day of the hanging will be a surprise. That is, The prisoner will not know which day it is until the executioner knocks on his cell door at noon on that very day. The prisoner, trying to outsmart fate, begins a process of elimination. He reasons that he cannot be hanged on Friday, because if he remains alive until Thursday night, only Friday will be left, and therefore the execution would not be unexpected. With Friday ruled out, he then concludes that if he gets to Wednesday night, Thursday would become the last possible day, and so a Thursday hanging would also not be a surprise. He applies the same reasoning recursively to eliminate Wednesday, Tuesday, and even Monday. Convinced by his deductive process, the prisoner concludes that the hanging cannot occur at all, only to be utterly astonished when, for example, the executioner arrives on Wednesday, catching him completely off guard. This paradox exposes the tension between logical reasoning and our intuitive understanding of surprise. On one hand, the prisoner's backward induction seems perfectly logical. If an event becomes predictable, it can no longer be surprising. Yet on the other hand, the very act of deducing that no day is possible creates the conditions for a genuine surprise when the execution occurs. The crux of the paradox lies in the notion of surprise. What does it really mean to be surprised? Does it mean that at the start of the week the prisoner has no basis for predicting the execution, or must he also remain unable to deduce it on the eve of the event? Different interpretations of surprise lead to different conclusions. Some analyses, like those found on Wolfram MathWorld, point out that if surprise is taken to mean that the prisoner cannot deduce the day in advance, then once he eliminates Friday, the very logic he employs might be self-defeating, because if he believes no day is possible, then any day on which the hanging occurs would indeed be unexpected. In more detailed discussions, scholars have attempted to formalize the paradox by introducing various definitions of expectation and surprise. One approach is to consider the prisoner's knowledge on different days. For instance, early in the week, the prisoner's uncertainty might be complete. He cannot rule out any day because he has not yet gathered any additional evidence. However, as the week progresses, if he remains alive, the set of possible days narrows. By Thursday night, if he has not been hanged, Friday appears inevitable, and thus a Friday execution would not be surprising. Yet, if the prisoner's reasoning leads him to conclude that no day is possible, then the actual occurrence of the execution on any day, say Wednesday, will catch him off guard precisely because he had convinced himself that his fate was logically impossible. This self-referential twist is what many find most intriguing about the paradox. Critics of the prisoner's reasoning argue that his backward induction is flawed because it depends on assumptions about his future state of knowledge. The prisoner assumes that if he survives until the day before a given day, he will be able to deduce that the execution must occur on the last remaining day, thereby voiding the element of surprise. However, this reasoning neglects the fact that his deductions are based on the judge's original statement, which itself is somewhat ambiguous. The judge promised a surprise but did not specify exactly how surprise should be measured or at what moment it must occur. For example, if surprise is defined relative to his knowledge at the very start of the week, then every day might still be surprising because his initial information did not allow him to eliminate any day with certainty. Alternatively, if surprise is determined by his state of mind the night before, then his elimination of Friday seems reasonable, but only if he can be absolutely sure that he will still be alive to make that deduction. In practice, the prisoner's reasoning is undermined by the uncertainty inherent in his situation. The fact that he can be caught off guard by an execution on, say, Wednesday, demonstrates that his chain of reasoning, while internally consistent to some extent, fails to capture the full dynamic of his evolving knowledge over the week. Moreover, some philosophers argue that the paradox highlights a deeper issue about self-reference and the limits of deductive reasoning. The prisoner's argument is akin to a self-referential statement. He is using the judge's promise that he will be surprised to predict that he will not be surprised, and thereby deducing that the execution cannot occur. Yet, if his deduction is accepted, the very conditions for being surprised are restored. In other words, if he convinces himself that an execution is logically impossible, then the arrival of the executioner becomes the ultimate surprise. This circularity is reminiscent of other well-known paradoxes such as the liar paradox, and shows that sometimes our intuitive concepts, like surprise or knowledge, resist complete formalization. Several modern treatments of the paradox have attempted to resolve it by dissecting these ambiguities. Some approaches involve probabilistic reasoning, suggesting that even if the prisoner can assign probabilities to each day, the inherent randomness of the judge's decision ensures that the execution will always have an element of unpredictability. Others have drawn on modal logic and the study of self-referential statements to demonstrate that the prisoner's reasoning, while seemingly valid on the surface, contains hidden assumptions that lead to a contradiction when taken to its logical extreme. Ultimately, the unexpected hanging paradox serves as a powerful reminder of the limits of logical deduction when applied to situations involving self-reference and future knowledge. The prisoner's attempt to use backward induction to eliminate all possible days is itself a kind of trap. The more he believes he can predict his fate, the more vulnerable he becomes to genuine surprise. This paradox does not have a universally accepted resolution. Rather, it continues to stimulate debate about the nature of expectation, surprise, and the structure of logical reasoning. Whether one views the paradox as a failure of the prisoner's deduction, an ambiguity in the meaning of surprise, or an illustration of deeper issues in epistemology and self-reference, it remains a rich and thought-provoking puzzle that challenges us to reconsider the limits of our own reasoning processes. In summary, the unexpected hanging paradox encapsulates the conflict between logical reasoning and human intuition. The prisoner's elegant but ultimately flawed argument shows that when we try to outsmart a statement that refers to our own knowledge, we can end up creating a situation where our very certainty becomes the source of our surprise. It reminds us that certain concepts, like surprise, are difficult to pin down with precise logic, and that sometimes the outcome of events can defy even the most careful deductions. The paradox endures not because it has a neat solution, but because it exposes the challenges of applying formal reasoning to the messy realm of human experience. The paradox of value, diamond water paradox. The paradox of value, also known as the diamond water paradox, is one of the most famous puzzles in economics that asks a seemingly simple question: why is water, which is essential for life, so cheap, while diamonds, which serve little practical purpose, are so expensive? At first glance, one might expect that the goods most necessary for survival would command the highest prices. In the classical view, water's life-sustaining qualities would imply enormous value, yet in the marketplace, water is abundant and inexpensive. In contrast, diamonds, while beautiful and desirable, have little to do with the necessities of life, yet their scarcity and the high demand for them push their prices to astronomical levels. The resolution of this paradox came with the development of marginal utility theory. The key insight is that price is not determined by the total utility of a good, but rather by its marginal utility. That is, the additional satisfaction or benefit derived from consuming one more unit. Although water has tremendous overall utility because it is essential for survival, its marginal utility is very low because it is so plentiful. In other words, once basic needs are met, an extra liter of water adds very little extra satisfaction. On the other hand, diamonds are rare, and because consumers have very limited access to them, the additional satisfaction from obtaining one more diamond is high, thereby driving up its price. This shift from considering total utility to marginal utility explains why non-essentials can be expensive despite having low overall usefulness, while essentials can be cheap due to their abundance. This paradox was noted by early economists such as Adam Smith, who found it puzzling in his seminal work, and later resolved by the marginal revolution spearheaded by economists like Carl Menger and William Stanley Jevons. Their theories showed that the subjective value of a good depends on individual preferences and the scarcity of that good, not merely on its ability to satisfy basic human needs. In modern terms, even though water is vital, its overwhelming supply means that consumers do not have to compete for it, so its marginal benefit, the extra satisfaction from an additional unit, is minimal. Conversely, because diamonds are rare, even a slight increase in quantity can provide a significant boost in satisfaction to someone who desires them, which explains their high market value. This concept has profound implications for understanding market behavior. It teaches us that prices are not determined solely by the intrinsic value of a commodity or its contribution to human welfare, but by how consumers value an extra unit relative to what they already have. This idea challenges a simplistic view of value based on necessity alone and underscores the importance of scarcity and consumer choice. It also provides a bridge between subjective and objective measures of value. While water is objectively necessary for life, the price mechanism in a free market reflects the subjective judgments of individuals who weigh scarcity, availability, and personal preference when making purchasing decisions. Furthermore, the diamond water paradox invites us to explore the relationship between total utility and marginal utility. Total utility refers to the overall benefit that a consumer derives from consuming a good, whereas marginal utility is the benefit from consuming one additional unit. In the case of water, even though the total utility is enormous, because without water, life would be impossible, the marginal utility diminishes rapidly as more water is consumed. Once a person has enough water to quench their thirst and meet basic needs, the benefit of an extra gallon is negligible. Diamonds, on the other hand, have low total utility since they are not essential, but their rarity means that each additional diamond represents a substantial increase in satisfaction for those who value them for their beauty, status, or other subjective reasons. The paradox of value also illustrates how the concept of scarcity is central to economic theory. Scarcity is not simply about the physical availability of a good, but also about the opportunity cost of using resources to produce that good. Since water is abundant, its production and distribution do not require the same level of resource allocation as diamonds, which are rare and often require significant effort and cost to extract and refine. This difference in production costs and resource allocation further reinforces the high price of diamonds relative to water, even though the overall importance of water is far greater in terms of sustaining life. Critics of the paradox have sometimes argued that it is merely a matter of semantics or a misinterpretation of what value truly means. However, the resolution through marginal utility provides a robust framework that has been tested and refined over time. By shifting focus from the aggregate importance of a good to the incremental benefit of each additional unit, economists were able to reconcile the apparent contradiction between necessity and price. This insight laid the groundwork for much of modern microeconomics and has influenced a wide range of economic policies and market analyses. In practical terms, the diamond water paradox can be observed in many everyday decisions. For example, while most people would agree that a steady supply of clean water is indispensable, in a situation where water is plentiful, individuals rarely assign a high price to it. In contrast, a luxury good like a high-quality watch or an exclusive piece of jewelry, much like diamonds, can command high prices because they are scarce and serve as symbols of status or personal achievement. Thus, the paradox helps explain why luxury items often have a price tag that seems disproportionate to their functional utility. They are valued for their rarity and the social signals they convey. The paradox of value not only deepens our understanding of market dynamics, but also challenges us to think critically about how we assess value in our lives. It reminds us that what is truly important is not necessarily reflected in its monetary price, and that economic value is often a matter of perspective. The apparent contradiction between the low price of water and the high price of diamonds is resolved when we consider that markets are driven by the marginal, not the total, benefits of goods. This insight has wide-ranging applications, from personal finance to public policy, and continues to influence how economists and policymakers approach issues of resource allocation and market regulation. In essence, the diamond water paradox is more than just a quirky puzzle. It is a cornerstone concept in economics that encapsulates the shift from classical to modern economic thought. By emphasizing the role of marginal utility, scarcity, and subjective value, the paradox challenges us to look beyond conventional wisdom and to appreciate the complex interplay between necessity, desire, and market dynamics. It demonstrates that prices are not always intuitive and that even the most essential goods can be undervalued if they are abundant, while less critical items can become expensive due to their rarity. This paradox, therefore, serves as a powerful example of how economic theory can illuminate the hidden forces that shape our world. Sorites paradox. The Sorites paradox, also known as the Heap paradox, is one of the most fascinating puzzles in philosophy and logic because it exposes the limitations of our everyday language when it comes to vague concepts. To explain it, imagine a large pile of sand, a heap. We all agree that a substantial collection of sand grains forms a heap. Now suppose you remove one single grain from that heap. Intuitively, nothing seems to change. One grain less doesn't alter the fact that it is still a heap. If you remove another grain, again, the overall impression remains the same. However, if you keep removing grains one by one, eventually you will be left with just a single grain of sand. At that point, it is clear that a single grain cannot be called a heap. The paradox asks, at what exact point does a heap cease to be a heap? This seemingly innocent question reveals a deep problem. Our language does not provide us with clear, unambiguous criteria for when something qualifies as a heap and when it does not. The word heap is an example of a vague predicate. There is no precise cutoff point in our natural use of the term, even though, if pressed, we might be forced to give an answer like, 1,000 grains make a heap. That number is arbitrary and fails to capture the gradual nature of the transition. In other words, because the change is incremental, the boundary between heap and non-heap is blurred. Historically, this paradox has its roots in ancient Greek philosophy. Eubulides of Miletus, a philosopher from the 4th century BCE, was one of the first to pose this problem, using it as an example to show that certain terms in our language are imprecise. Over the centuries, the heap paradox has been discussed by countless philosophers and logicians as they tried to reconcile the gap between the binary nature of classical logic and the fuzzy boundaries inherent in everyday concepts. One influential way to resolve, or at least to address, the Sorites paradox is through the lens of fuzzy logic. Unlike classical logic, where statements are either true or false, fuzzy logic allows for degrees of truth. In this framework, instead of saying this collection of sand is a heap as a yes or no proposition, we can say that a collection of 10,000 grains might be 0.95 heap-like, whereas a collection of 10 grains might be only 0.1 heap-like. This continuous scale accepts that there is a gradual transition from non-heap to heap without forcing a sudden, sharp division. Fuzzy logic thereby aligns more closely with our intuitive understanding that many of our everyday concepts are not strictly black or white, but lie on a spectrum. Another approach is known as epistemicism. According to this view, there is indeed a precise point at which a collection of grains stops being a heap, but that precise number is inherently. Epistemicists argue that classical logic remains intact and that every vague term actually does have an exact cutoff point, even if we are not capable of knowing it. This view satisfies the demand for precision demanded by traditional logic. However, it can feel counterintuitive because it implies that something as mundane as heap actually has a hidden, precise boundary, a number that, if we knew it, would allow us to say definitively when a heap turns into a non-heap. The implications of the Sorites paradox stretch far beyond just heaps of sand. Consider other vague concepts like bald. If one hair does not make a person bald, how many hairs must be removed before someone is considered bald? Similarly, how many years of education does it take before a person is considered educated? In these cases, the paradox shows that many of the categories we use in everyday language have fuzzy boundaries, which can lead to problems in legal reasoning, ethical debates, and even in the formulation of public policy. Laws and regulations often rely on terms like reasonable, significant, or substantial, and the vagueness inherent in these terms can lead to ambiguity in their application. For instance, if a law states that an action is punishable only if it causes significant harm, determining what counts as significant may be as challenging as figuring out the exact point where a heap ceases to be a heap. In modern computer science and artificial intelligence, the Sorites paradox also plays a role in dealing with imprecise or uncertain data. When algorithms attempt to classify or make decisions based on inputs that do not have clear-cut boundaries, such as natural language processing or image recognition, they face challenges similar to those posed by the heap paradox. Researchers in these fields have developed techniques like fuzzy set theory and probabilistic reasoning to handle the gradual transitions that are characteristic of many real-world phenomena. These methods allow systems to operate effectively even when the data do not fit into neat binary categories. The paradox thus serves as a reminder of the limitations of our classical binary logic when faced with the real-world continuum. It shows that our language, while incredibly useful, is sometimes too imprecise for the rigorous demands of logic. The debate between approaches like fuzzy logic and epistemicism reflects broader philosophical questions about the nature of truth and the adequacy of our conceptual frameworks. Are our everyday terms merely convenient approximations of more precise, hidden realities? Or should we embrace a more nuanced, gradient view of truth, where things are not simply true or false, but have varying degrees of applicability? One particularly interesting implication of the Sorites paradox is its challenge to the way we form categories in our minds. We naturally tend to divide the world into distinct, well-defined categories, but the paradox reveals that many of these divisions are, in fact, arbitrary. This insight can have a profound impact on how we think about knowledge itself. It suggests that some of the boundaries we take for granted, whether in science, ethics, or everyday life, might be more flexible and context-dependent than we realize. Furthermore, the paradox has influenced discussions in epistemology, the study of knowledge, and the philosophy of language. It raises questions about how meaning is determined in language and whether some terms can ever be given a precise definition. The challenge posed by the Sorites paradox forces us to confront the idea that our concepts might be inherently indeterminate, leading to broader questions about how we can know anything with absolute certainty. In summary, the Sorites paradox, or Heap paradox, is more than just a quirky puzzle about grains of sand. It is a window into the challenges of dealing with vagueness in language and thought. Whether you lean toward a solution based on fuzzy logic, accepting that many concepts exist on a continuum, or toward an epistemic view that posits an exact but unknowable boundary, the paradox highlights the tension between our intuitive, everyday use of language and the strict demands of formal logic. It reminds us that many of our concepts, from what it means to be tall or rich to what qualifies as do not have clear, binary distinctions. This realization has far-reaching implications in philosophy, law, computer science, and beyond, challenging us to develop more flexible, nuanced approaches to understanding the world. Ultimately, the Sorites paradox invites us to embrace the uncertainty and fluidity inherent in our language, and to recognize that sometimes the beauty of our concepts lies in their very vagueness, rather than in an elusive precision. The paradox of tolerance. The paradox of tolerance is a provocative idea that challenges the very limits of an open, free society. It was most famously articulated by Karl Popper, who argued that unlimited tolerance, if extended even to those who are openly intolerant, can ultimately lead to the demise of tolerance itself. The central insight is that if a society tolerates every ideology without restraint, it also tolerates ideas that seek to suppress tolerance, silence dissent, and even overthrow democratic institutions. In essence, by allowing extremist and intolerant views to flourish unchecked, a tolerant society may eventually empower those very forces that would dismantle the framework of openness and freedom. Imagine a society that prides itself on free speech, open debate, and the protection of all viewpoints. In such a society, citizens are encouraged to express even unpopular opinions, as long as they do not incite violence or hatred. But what happens when an extremist group, whose ideas are fundamentally opposed to these values, starts using the platform provided by that very tolerance? If the state continues to allow this group to speak freely without any restrictions, the extremist ideology may gain traction and ultimately become strong enough to challenge and even overthrow the democratic system. Popper warned that to safeguard a tolerant society, it might be necessary to exercise a form of defensive intolerance against those who are determined to destroy tolerance from within. This does not mean suppressing dissenting opinions in general, but rather drawing a clear line against ideologies that aim to eliminate the very conditions that allow for free and open discourse. Critics of Popper's view sometimes argue that if you start limiting tolerance, you risk sliding into authoritarianism, where even legitimate criticism might be silenced. However, the counterargument is that when intolerance itself becomes a political force, it is not merely another opinion to be debated, but a destructive power that can erode the fundamental rights of individuals. In such cases, allowing intolerant ideologies to flourish becomes self-defeating, because these ideologies are designed to dismantle the pluralistic and open society that initially allowed them to express themselves. Therefore, a tolerant society must have the resolve to exclude or counteract those who use tolerance as a cover for their own intolerant agenda. This is not an arbitrary suppression of speech, but a strategic defense of the very principles of freedom and open debate. The paradox also raises complex questions about the nature of free will and the dynamics of social order. If individuals in a tolerant society are free to express any opinion, then they might also express views that, if allowed to proliferate, would fundamentally undermine the society's ability to remain tolerant. The challenge lies in determining where to draw the line. What constitutes intolerant? Where do we differentiate between extreme opinions that are merely unpopular and those that actively seek to dismantle the rights of others? Popper did not suggest that society should become intolerant of all dissenting views. Rather, he argued that society should reject those forms of intolerance that are committed to destroying the fabric of an open society. This nuanced position implies that while a wide range of opinions should be allowed, there must be a threshold beyond which ideas become dangerous because they are not simply different, but are actively harmful to the core values of tolerance and democracy. One practical example of the paradox can be seen in debates over hate speech and extremist propaganda. In many democratic societies, there is vigorous debate about whether certain forms of hate speech should be legally restricted. Proponents of absolute free speech argue that any restriction is a slippery slope towards censorship. However, defenders of Popper's perspective contend that if hateful and intolerant speech is allowed to spread, it may embolden those who would ultimately use violence or coercion to silence opposition. Thus, a balance must be struck. While a society should generally allow freedom of expression, it must also be vigilant in preventing the spread of ideas that could lead to the destruction of that very freedom. The paradox of tolerance is not merely an abstract philosophical puzzle. It has real-world implications. Consider, for example, the challenges faced by modern in dealing with extremist groups that use social media to spread their message. When a state chooses to allow all voices, it might inadvertently provide a platform for those who would undermine democratic norms. This raises the difficult question of how to protect a society's openness while also defending it from the corrosive effects of intolerant ideologies. The debate is far from settled, and it forces us to re-examine our assumptions about the limits of tolerance, the role of free speech, and the responsibilities of a democratic society. Moreover, the paradox invites us to think about the long-term consequences of our political choices. Tolerance, when applied without limits, can lead to a situation where the forces that are supposed to protect a society end up being eroded from within by those who exploit that very openness. In this sense, the paradox serves as a cautionary tale, A society that is too permissive may ultimately pave the way for its own downfall. Popper's argument is a call to action for citizens and policymakers alike, to be vigilant, to set clear boundaries against intolerant ideologies, and to ensure that the values of freedom and open debate are preserved for future generations. In summary, the paradox of tolerance challenges us to reconcile the ideal of an open society with the practical necessity of defending that society against destructive forces. It reminds us that while freedom of expression is a cornerstone of democracy, it is not an absolute right that can be extended without limits. If a society tolerates the intolerant to the point where they can gain power and suppress dissent, then the very foundation of tolerance is undermined. The paradox thus forces us to confront the uncomfortable reality that in order to maintain a tolerant society, we may sometimes need to be intolerant of intolerance, a delicate balance that remains at the heart of modern political debate. This ongoing discussion highlights the complexities inherent in designing a just and free society, and it continues to influence contemporary debates over free speech, censorship, and the role of government in protecting democratic values. The Raven Paradox. Hempel's Raven Paradox is a thought experiment that forces us to rethink what counts as evidence for a general statement. Consider the simple hypothesis, all ravens are black. In classical logic, this statement is logically equivalent to its contrapositive, everything that is not black is not a raven. At first glance, it seems that every time you observe a black raven, you are confirming the hypothesis. But here is where the puzzle begins. According to logical equivalence, observing any non-black object that is not a raven, say, a green apple, should also count as evidence in favor of all ravens are black. This conclusion appears absurd because it implies that mundane observations, like seeing a green apple or a red car, somehow confirm a claim about birds. To explain the paradox in more depth, imagine that you set out to test the hypothesis, all ravens are black. The most natural evidence you would consider is a direct observation of ravens, noting whether they are black or not. Finding a black raven seems like very strong confirmation because it is directly relevant to the claim. Yet, by the rules of classical logic, the contrapositive tells us that any object that is not black and also not a raven supports the claim. This means that every non-black object in the world, from a white wall to a blue notebook, becomes evidence, even if in a very diluted sense. The intuition that only observations of ravens should matter is at odds with the formal equivalence of the statements. Our everyday notion of evidence appears selective, favoring observations that are directly connected to the subject, while formal logic treats all confirming instances equally regardless of their context. One way to resolve this tension is to recognize that while both types of observations are logically equivalent, they do not carry the same weight in terms of how much they should alter our degree of belief. This idea is captured by Bayesian confirmation theory, which tells us that we update our beliefs based on the likelihood of observing the evidence if the hypothesis were true versus if it were false. A black raven is far more probable under the assumption that all ravens are black than if the hypothesis were false, so seeing a black raven dramatically increases our confidence. In contrast, green apples or any non-black, non-raven objects are so common that their observation hardly changes our overall belief. In effect, although every observation of a non-black object that is not a raven is formally confirming evidence, its impact on our degree of belief is negligible compared to the impact of directly observing ravens. This nuance helps reconcile the logical equivalence with our intuitive sense that only directly relevant evidence should matter. Another approach to the paradox is to focus on the notion of relevance. When we say all ravens are black, we are typically interested in evidence that speaks directly about ravens. Observing a raven, especially a black one, feels immediately relevant. However, a green apple seems remote. Its connection to the hypothesis is only indirect, through logical equivalence, not through any direct association with the concept of raven. Some philosophers argue that our criteria for confirmation should include a notion of relevance or context. Under this perspective, while it is true in a purely formal sense that a non-black, non-raven confirms the contrapositive, such evidence is weighted so low in relevance that it practically does not affect our confirmation of the hypothesis. In everyday practice, we ignore evidence that is logically relevant but practically insignificant. The paradox also invites us to consider the limitations of our language and conceptual frameworks. The statement, "all ravens are black," is deceptively simple. But when we scrutinize what it means to confirm a universal claim, we see that our language is filled with vagueness. Terms like raven and black may seem well defined at first, but there are edge cases and ambiguities. For instance, what about a raven that is slightly faded, or an object that is almost black but not quite? Such questions hint at the broader issue of how we use language to form generalizations and how those generalizations are tested against observations. Some scholars have proposed formal approaches, like fuzzy logic, to deal with the vagueness inherent in many of our concepts. In fuzzy logic, instead of a binary classification, an object is either black or not black, a bird is either a raven or not, we allow for degrees of membership. Under such a system, a particular observation might only partially confirm a hypothesis, and the strength of the confirmation can vary. While this approach does not eliminate the raven paradox, it does provide a framework for understanding how evidence might be graded rather than treated as all or nothing. There are also epistemic interpretations that suggest our intuitive reaction is a matter of how we process information. When we observe a non-black object that isn't a raven, we intuitively consider it irrelevant because it lies outside the domain of what we care about: ravens. In contrast, the observation of a black raven directly impacts our assessment of the hypothesis. In this view, our cognitive processes are tuned to give more significance to evidence that is contextually appropriate, even if, strictly speaking, all evidence might be logically equivalent. This insight reminds us that human reasoning is not merely a mechanical application of formal logic. It also involves judgments about relevance, salience, and context. The broader implications of Hempel's raven paradox extend to how we conduct scientific in science. Gathering evidence for a theory is not just about accumulating data that fits a logical form. It is also about assessing the quality, relevance, and context of that data. The paradox highlights that the process of confirmation is inherently complex, requiring us to consider not only whether evidence supports a hypothesis in principle, but also how strongly it does so in practice. This has led to more refined methods in the philosophy of science and statistical inference, where the impact of each piece of evidence is measured by its ability to shift our overall confidence, rather than by its mere logical compatibility with the hypothesis. In addition, the paradox has sparked debates about the nature of confirmation and the structure of scientific reasoning. It challenges the idea that logical equivalence is sufficient for confirming a hypothesis and pushes us to consider alternative models where the context and degree of relevance are taken into account. Whether one adopts a Bayesian approach, a fuzzy logic perspective, or some other method, the central lesson is that evidence is not all created equal. Its importance depends on its directness and its impact on our overall understanding of the subject. Ultimately, Hempel's Raven Paradox is not just an abstract puzzle about birds and apples. It is a window into the complexities of how we understand the world, gather evidence, and form beliefs. It shows that even a statement as seemingly straightforward as "all ravens are black" can hide deep challenges when we try to determine what evidence truly confirms it. The paradox forces us to confront the gap between formal logic and human intuition, revealing that our everyday reasoning about confirmation and evidence is more nuanced than strict logical equivalence would suggest. In grappling with this paradox, we learn that our methods for assessing truth must account for both logical structure and contextual relevance, a lesson that resonates across philosophy, science, and everyday life. The paradox of fiction. The paradox of fiction challenges our understanding of emotional response by asking how we can be deeply moved by characters and events we know to be entirely invented. It begins with the seemingly plausible idea that to feel genuine emotions such as pity, fear, or we must believe in the real existence of the entities that evoke these feelings. Yet when we engage with a novel, film, or play, we are fully aware that the characters and events are fabrications, and still we experience a profound emotional resonance. This tension raises the question of whether our emotional reactions are somehow irrational, or whether our understanding of what it means to believe in something needs to be reconsidered. One influential formulation of the paradox relies on three premises. First, it appears that emotional responses are contingent upon the belief that the object of our emotion actually exists. Second, when we interact with a work of fiction, we know that the characters and events do not exist in any literal sense. Third, despite our awareness of the fictionality of these works, we still find ourselves emotionally engaged and moved. If all three premises are taken at face value, a contradiction seems inevitable. We are emotionally affected by things that we simultaneously do not and do not believe to exist. This puzzle has sparked extensive debate among philosophers and psychologists, leading to several different proposed resolutions. One approach, often associated with Kendall Walton's make-believe theory, argues that our emotional responses to fiction are not genuine in the ordinary sense, but are instead what Walton calls quasi-emotions. In this view, when we watch a film or read a novel, we participate in a game of make-believe in which we temporarily adopt a set of fictional propositions as if they were true. We do not come to believe in the literal existence of the characters or events. Instead, we imagine them in a way that allows us to experience feelings similar to those we would have if they were real. This imaginative engagement does not undermine the intensity of our responses, but recasts them as part of an elaborate, shared convention of fiction appreciation. Rather than a failure of reason, the emotional impact of fiction is understood as a feature of our capacity to engage with symbolic representations and to simulate experiences internally. Another line of thought, sometimes labeled the thought theory, challenges the initial assumption that genuine emotional responses necessarily require belief in the existence of their objects. Proponents of this view suggest that emotions can be triggered not by literal belief in an entity's reality, but by a kind of imaginative representation or mental simulation of that entity. When we read about a tragic hero or a frightening monster, we do not need to believe that the person or creature exists in the external world. Instead, we entertain a vivid representation in our mind. This process of imaginative engagement is sufficient to evoke genuine feelings, meaning that the conditions for a proper emotional response do not hinge on the existence of the object in a material sense. According to this perspective, our emotional lives are complex and do not strictly adhere to a simple true or false dichotomy about existence. A third perspective, sometimes called the illusion theory, posits that during our engagement with fiction, we experience a kind of temporary suspension of disbelief. This suspension is not so much an act of deception as it is an active, willing embrace of a fictional reality. In this state, the boundaries between the real and the fictional are blurred, allowing us to respond as though the fictional world were real, even though we are cognitively aware that it is not. The power of narrative, vivid imagery, and skilled performance in literature and film can create an immersive experience in which the emotions we feel are not diminished by our knowledge of the fiction. This idea of a willing suspension of disbelief suggests that our capacity to respond emotionally to fiction is adaptive, and that our cognitive systems are capable of flexibly shifting between different modes of engagement depending on context. Despite these theoretical approaches, the paradox of fiction remains a vibrant topic of discussion, partly because it raises important questions about the nature of emotion, belief, and imagination. It challenges us to consider whether the standards for what counts as a genuine emotion might need to be broadened to include responses elicited by representations that are known to be untrue. Moreover, recent discussions have extended the paradox to new media such as video games, where the interactive nature of the experience further complicates the issue. In video games, players not only observe but also actively participate in the unfolding narrative. They make choices, control characters, and even influence outcomes within a clearly fictional world. This interactivity raises additional questions. When a player feels fear while maneuvering through a virtual maze or empathy for a digital character in distress, are those responses any less real because the events are simulated? And does the ability to affect the course of the narrative alter the way we experience the emotion? The exploration of the paradox in interactive contexts suggests that our emotional engagement with fiction is even more multifaceted than previously thought. It appears that our brains are capable of processing fictional scenarios in ways that parallel our responses to real-life events, utilizing similar neural and physiological pathways. This has been demonstrated in studies that measure heart rate, skin conductance, and brain activity while participants engage with both fictional and real-life stimuli. The evidence indicates that while there may be quantitative differences in the intensity of our responses, the qualitative experience of emotion in response to fiction shares much with our reactions to genuine occurrences. Such findings challenge the notion that belief in literal existence is a necessary condition for emotional involvement. Ultimately, the paradox of fiction invites us to rethink the relationship between cognition and emotion. It encourages a view of our mental lives as being highly adaptive, capable of generating meaningful responses even in contexts that are known to be constructed or simulated. Whether through the lens of make-believe, imaginative simulation, or a temporary lapse into an illusory state, the phenomenon reveals the remarkable power of narrative to shape our inner experiences. It reminds us that our emotional lives are not confined solely to interactions with the physically real world, but extend into the realm of art, literature, and media, where the play of ideas and images can have profound and lasting effects. In this sense, the paradox of fiction is not a flaw in our emotional architecture, but a testament to the complexity of human creativity and the capacity for meaning-making in all its forms. The paradox of analysis. The paradox of analysis arises from a tension at the heart of conceptual inquiry. On one hand, a correct analysis of a concept must capture precisely what that concept means, rendering it logically equivalent to the original. On the other hand, for an analysis to be genuinely informative, it must reveal something new or non-obvious about the concept, something that goes beyond a mere restatement of what was already known. If the analysis is correct in the strict sense that it is interchangeable with the concept being analyzed, then it appears trivial and uninformative. However, if it is crafted to be informative, it seems to depart from the original meaning and therefore cannot be deemed a correct analysis. This apparent contradiction, sometimes known as the Langford-Moore paradox, has sparked extensive debate among philosophers regarding what it means to analyze a concept and how such an analysis might be evaluated. The traditional view of conceptual analysis in analytic philosophy holds that by breaking a concept down into its constituent parts, or by explicating the conditions under which it applies, one can arrive at a clearer understanding of its content. For example, when one attempts to analyze the term bachelor, a common approach is to define it as an unmarried man. At first glance, this appears both correct and informative. It tells us precisely what is meant by the term and seems to provide insight into the structure of the concept. Yet, if bachelor and unmarried man are truly equivalent, then the analysis is nothing more than a restatement, offering no additional understanding beyond what we already assumed. This raises the question of whether there is any meaningful work being done in the process of analysis, or whether it merely labels the concept with a different expression without deepening our insight. One line of thought argues that our ordinary use of concepts is marked by an implicit, often unarticulated understanding of meaning. In this view, people may competently use a term like bachelor without being explicitly aware of all the underlying conditions that govern its application. The task of the philosopher, then, is to uncover and articulate these hidden assumptions in a way that makes the underlying structure of our thought transparent. However, if these underlying assumptions are already fully embedded in the concept itself, then a proper analysis, once it is completed, will be analytically equivalent to the original concept. The paradox then emerges because the very success of the analysis, the fact that it leaves the concept unchanged in its core content, renders it uninformative. If the analysis is simply a restatement in different words, how can it claim to yield new insights or a deeper understanding? Some philosophers have proposed that the solution to the paradox lies in rethinking the nature of informativeness. They suggest that an analysis can be informative not by adding new content to the concept, but by making explicit aspects of our implicit knowledge that we might not have been able to articulate before. In other words, while the analysis may be equivalent to the original concept, it transforms our tacit competence into explicit knowledge. This transformation can have epistemic value because it enables us to see hidden connections and to resolve ambiguities that were previously taken for granted. For instance, while everyone may use the term bachelor correctly in everyday discourse, a detailed analysis might reveal subtle distinctions between social and biological aspects of being unmarried that have implications for moral or legal reasoning. In this way, the analysis can be seen as providing a kind of meta-knowledge, a knowledge about the structure and use of our concepts, rather than knowledge about the external world. Another response to the paradox is to challenge the assumption that correctness in analysis must entail complete synonymy between the analyzed concept and its analysis. Some theorists argue that a concept can be analyzed in a way that captures its core meaning while still leaving room for peripheral or contextual nuances. Under this approach, the analysis does not aim to capture every possible aspect of a concept, but rather to identify a stable and widely shared central meaning. The residual or contextual aspects might then be seen as decorations on the core, which can vary from one usage to another. Although this view preserves some degree of informativeness, it risks a charge of circularity if the distinction between the core and the periphery is not itself clearly established. A further line of thought comes from the work of philosophers who question whether there is any non-circular way to perform conceptual analysis at all. Quine famously challenged the analytic-synthetic distinction, arguing that no clear boundary exists between truths that are true by virtue of meanings and those that are true by virtue of facts about the world. If the very notion of a concept having an analytic content is undermined by such skepticism, then the paradox of analysis might dissolve by undermining one of its basic premises. In this view, the idea that an analysis must be both correct, in the sense of capturing the same meaning, and informative, in the sense of revealing something new, is a mistaken expectation. Instead, our understanding of concepts is inherently holistic and subject to revision in light of new evidence and new theoretical frameworks. The paradox of analysis thus forces us to confront deep questions about the nature of meaning and the function of conceptual inquiry. It reveals the challenge of making explicit the structure of our thought without either trivializing it or, conversely, corrupting it by introducing extraneous elements. While some resolutions emphasize the importance of explicating tacit knowledge and rendering implicit assumptions explicit, others focus on the need to abandon a rigid requirement for synonymy in favor of a more flexible, graded understanding of conceptual equivalence. Ultimately, the paradox serves as a reminder that our cognitive and linguistic practices are more complex than simple definitions might suggest, and that the process of analysis is not merely a matter of substituting one set of words for another, but of reflecting on how we structure our understanding of the world. In grappling with the paradox of analysis, philosophers are not merely engaging in an abstract puzzle, but are addressing the core of how we come to know and articulate the concepts that shape our thinking. The debate over whether a correct analysis is necessarily trivial or whether it can yield genuine insight touches on broader issues in epistemology and the philosophy of language, such as the nature of implicit versus explicit knowledge, the limits of linguistic expression, and the interplay between our intuitive grasp of meaning and its formal articulation. Although there is no universally accepted resolution to the paradox, its persistent presence in philosophical discussion underscores the ongoing challenge of articulating precisely what it means to understand a concept and how such understanding contributes to our broader intellectual endeavors. The paradox of analysis, therefore, is not a simple anomaly to be dismissed, but a central and enduring problem that continues to provoke reflection on the methods and aims of philosophy itself. It invites us to consider the extent to which our concepts are fixed or malleable, and how the process of making our implicit knowledge explicit can enrich our understanding even if it does not add new content in the traditional sense. By examining this paradox, we gain insight not only into the nature of concepts, but also into the broader challenges of philosophical inquiry, where the search for clarity and precision often runs headlong into the very limitations of language and thought. The Monty Hall problem. The Monty Hall problem is a probability puzzle that has confounded many people since it was popularized by the television game show Let's Make a Deal. Imagine you are a contestant on the show and are presented with 3 closed doors. Behind one door is a desirable prize, such as a car, while behind the other 2 doors are goats. You are asked to select one of the 3 doors, and once you make your choice, the host, who knows what is behind every door, opens one of the 2 remaining doors to reveal a goat. At this point, you are given the opportunity to either stick with your original choice or switch to the other unopened door. Although it might seem at first glance that it does not matter whether you switch or stay, the surprising solution to the puzzle is that you should always switch because doing so gives you a 2/3 chance of winning the car, while sticking with your initial choice only gives you a 1/3 chance. To understand why this is the case, it helps to think about the problem from the beginning. When you first choose a door, there is a 1 in 3 chance that you have picked the door with the car and a 2 in 3 chance that the car is behind one of the other 2 doors. The key element is the host's action, which is not random, but is instead based on knowledge of what lies behind the doors. Because the host will always reveal a goat, his choice provides additional information about the remaining unopened doors. If you initially picked the door with the car, which happens with probability 1/3, then switching would lead you to a goat. However, if you initially picked a door with a goat, which happens with probability 2/3, then the host's action of revealing the other goat leaves the car behind the remaining door, and switching would win you the car. Therefore, by switching, you effectively win in 2 out of the 3 equally likely scenarios. This counterintuitive result can be illustrated through various approaches. One common method is to simulate the game repeatedly. If you imagine playing the game 300 times, you would expect that in approximately 100 of those games, your first pick would be the car, and in the remaining 200 games, your first pick would be a goat. In the 100 games where your initial choice was correct, switching would cause you to lose the car. But in the 200 games where you initially chose a goat, switching would lead you to win the car, meaning that by switching you would win approximately 2/3 of the time. This large sample simulation reinforces the mathematical reasoning behind the solution. Another way to grasp the logic behind the Monty Hall problem is to extend it to a scenario with many more doors. Suppose instead of 3 doors, you are presented with 100 doors, with 1 door hiding a car and the remaining 99 hiding goats. After you choose 1 door, the host, knowing what is behind every door, opens 98 other doors, all showing goats. Now, only your chosen door and 1 other door remain closed. Initially, there was only a 1% chance that you chose the car and a 99% chance that the car was behind one of the other doors. When the host opens 98 doors, the entire 99% probability that the car was among the other doors collapses onto the single remaining closed door. In this extended version, it becomes much clearer that switching dramatically increases your odds of winning from 1% to 99%, and the same logic applies in the 3-door version of the problem. The counterintuitive nature of the Monty Hall problem lies in our natural tendency to assume that the odds must be equal once a door has been opened. Many people mistakenly believe that after the host reveals a goat, there are 2 doors left, and therefore a 50-50 chance of winning. This mistake arises from a failure to account for the fact that the host's action was not random. It was specifically designed to reveal a losing option. Because the host always reveals a goat, his action influences the probabilities associated with the remaining doors. Instead of simply splitting the remaining probability equally, the host's intervention redistributes the likelihood in a way that favors switching. Critics of the solution sometimes argue that the problem is ambiguous, or that the outcome depends on hidden assumptions about the host's behavior. It is important to note that the standard formulation of the Monty Hall problem assumes that the host always opens a door with a goat and always offers the option to switch, regardless of the contestant's initial choice. In variations of the problem where the host's behavior is not consistent, or where there is a chance that he might not offer the switch, the probabilities can indeed change. However, in the classical version of the problem, the host's consistent behavior is what makes the analysis work. The Monty Hall problem is not just a quirky brain teaser. It has significant implications for understanding probability theory and decision-making under uncertainty. It demonstrates that human intuition about probability can be flawed, and that careful analysis of conditional probabilities is essential in making optimal decisions. This problem has been widely discussed in academic circles, and it serves as a popular example in courses on probability and statistics, as well as in discussions about rational choice and game theory. Moreover, the problem encourages us to think about how information is processed and how decisions are made when additional information is revealed. In real-world situations, similar dynamics can occur when new data or evidence emerges, prompting a reassessment of initial beliefs. The lesson of the Monty Hall problem is that revising decisions in light of new information, when that information is provided in a structured and predictable way, can lead to better outcomes than simply sticking with initial choices. This insight is applicable in a wide range of fields, from economics and finance to psychology and everyday decision-making. In summary, the Monty Hall problem illustrates that the optimal strategy in a situation where a host, who knows the outcomes, reveals additional information is to always switch your initial choice. Although our intuition might lead us to believe that the odds become evenly split after one losing option is revealed, a deeper analysis shows that switching increases the probability of winning from 1/3 to 2/3. This problem not only challenges our intuitive grasp of, but also serves as a powerful reminder of the importance of incorporating new information into our decision-making process. Its lessons continue to resonate in various domains, emphasizing the need for rigorous analytical thinking in situations of uncertainty and the value of re-evaluating our initial assumptions in light of fresh evidence. The lottery paradox. The lottery paradox presents a fascinating challenge to our understanding of rational belief and epistemic justification. Imagine a fair lottery with, say, 1 million tickets, where exactly one ticket wins and the remaining 999,999 for any single ticket. The chance of losing is so overwhelmingly high, nearly 1, that it appears entirely rational to believe that that particular ticket will lose. If you consider each ticket in isolation, you have good reason to accept, based on probability, that it is not the winning ticket. However, if you apply this reasoning uniformly to every ticket in the lottery, you end up with the contradictory conclusion that all tickets will lose, which is impossible because the very structure of the lottery guarantees one winner. This conflict between individually justified high-probability beliefs and their collective inconsistency is what constitutes the lottery paradox. The paradox forces us to confront a core issue in epistemology. The tension between the notion that rational belief can be based on high probability and the principle of deductive closure. The idea that if you accept a set of propositions, you should also accept all of their logical consequences. In the case of the lottery, while it is individually reasonable to believe of any given ticket that it will lose, the deductive closure of these beliefs leads to an outright contradiction because we know that at least one ticket must win. Thus, the paradox suggests that if we simply accept every proposition that is highly probable, we risk ending up with an inconsistent set of beliefs. One way to illustrate this problem is to consider the following scenario. Suppose you set a threshold for rational belief. You decide that you will accept any proposition that has a probability of 99.99% or higher. For each lottery ticket, the probability of losing is 99.99%, so it seems rational to accept, for every ticket, that it will lose. Yet, if you aggregate these beliefs, you are forced to conclude that every ticket loses, contradicting the known fact that one ticket wins. This outcome challenges the idea that high probability alone is sufficient for rational acceptance and highlights the need for a more nuanced understanding of belief. Philosophers have proposed various responses to this paradox. One approach is to distinguish between what it means to believe something and what it means to accept it. In everyday life, we might operate on a provisional level of acceptance where we treat highly probable propositions as if they were true for practical purposes without committing to them in an absolute sense. Under this view, while it is rational to act as if each lottery ticket will lose, we might refrain from formally aggregating these beliefs into a single, closed system. In other words, our cognitive system could be thought of as non-monotonic, allowing for the withdrawal or revision of beliefs when they lead to inconsistencies. By not demanding deductive closure for our set of high-probability beliefs, we can avoid the paradox while still functioning effectively in everyday decision-making. Another response centers on the idea that rational acceptance may require more than just a numerical probability threshold. It may be that the criteria for accepting a belief should involve contextual factors and the potential consequences of accepting the belief collectively. For example, while it is individually rational to assume that any one lottery ticket will lose, one might adopt a different standard when considering a group of such propositions. A rational agent could recognize that while each ticket is almost certainly a loser, the structure of the lottery as a whole precludes the possibility of all tickets being losers. This perspective suggests that the context in which beliefs are held matters greatly, and that our epistemic standards must account for the interplay between individual probabilities and collective outcomes. A further consideration is the distinction between subjective probability and objective certainty. High probability does not equate to certainty, and thus holding a belief with high probability should perhaps be seen as a tentative commitment rather than an unequivocal acceptance. In a lottery, each ticket losing is almost certain, but not absolutely so. The minuscule chance of any single ticket winning means that our individual beliefs must remain open to revision. This open-endedness may be sufficient to avoid the paradox, as it prevents us from logically deducing that every ticket will lose. In other words, our rational beliefs might be better modeled as degrees of confidence that do not automatically combine in a way that enforces deductive closure. The lottery paradox also has significant implications for theories of knowledge. It raises the question of whether knowledge requires absolute certainty, or if a body of highly probable beliefs can constitute knowledge even when their combination leads to inconsistency. Some epistemologists argue that knowledge should be understood in terms of practical success and reliability rather than strict logical. Under this pragmatic view, it is acceptable to act on beliefs that are nearly certain even if, in theory, the conjunction of such beliefs might be inconsistent. This perspective aligns with the idea that our cognitive systems are designed to function effectively in the real world, where uncertainty is the norm and absolute certainty is rarely attainable. Critics of the lottery paradox sometimes argue that the problem is not so much a failure of rationality as it is a misapplication of the principles of deductive closure to a domain where they do not properly belong. They suggest that our intuitions about probability and belief are inherently context-sensitive, and that the rules governing rational acceptance in everyday situations should not be expected to align perfectly with the strictures of classical logic. Instead, rational belief may be understood as a flexible and context-dependent notion that does not demand absolute closure. This view encourages a more sophisticated model of epistemic reasoning, one that can accommodate high-probability judgments without requiring that they be logically compounded in a way that leads to contradiction. The enduring interest in the lottery paradox lies in its ability to illuminate the limitations of our intuitions about rational belief and the structure of our knowledge. It challenges us to refine our understanding of what it means to hold a belief, how we justify those beliefs, and how they interact within our overall epistemic framework. By grappling with the paradox, philosophers have been able to develop more nuanced theories of belief acceptance, including approaches that allow for defeasible reasoning and context-sensitive standards. These developments have had far-reaching consequences, not only for epistemology, but also for fields such as decision theory and the philosophy of language, where similar issues about certainty, probability, and logical consistency arise. Furthermore, the lottery paradox has practical applications in real-world decision-making. In contexts where individuals must act under uncertainty, such as in finance, medicine, or public policy, the challenge of aggregating high-probability beliefs without falling into inconsistency is a critical issue. For instance, when evaluating risk in medical diagnoses or financial investments, one must often rely on probabilistic assessments that, if taken in isolation, seem entirely reasonable, but may lead to erroneous conclusions when combined without careful consideration of the overall structure. The lessons of the lottery paradox remind us that even highly reliable individual indicators can, when aggregated improperly, lead to misleading or even disastrous outcomes. The paradox of self-amendment. The paradox of self-amendment arises from a troubling tension at the heart of any system that is designed to modify its own rules. Imagine a constitution or formal set of rules that explicitly includes a provision authorizing its own amendment according to a prescribed process. At first glance, this self-amendment clause appears to be a mark of flexibility, allowing the system to adapt over. Yet if the system can amend its own rules, then it seems it should be able to amend even the very rule that allows such amendments. In other words, a system that permits self-amendment may, if taken to its logical conclusion, also permit its own amendment procedure to be repealed or altered. But if that happens, then the process by which the amendment was made loses its legitimacy, since its validity was originally contingent upon that very procedure remaining in force. This creates a circularity. For the system to be self-amendable, it must both preserve and be subject to change, and it is precisely the ability to change that undermines the permanence of the amendment rule itself. One way to see the problem is to consider a hypothetical constitution that contains a clause stating, "This constitution may be amended in accordance with the procedure set out in Article X." On the surface, this clause is intended to allow the legal order to evolve in response to new circumstances. However, if a successful amendment is later proposed that would repeal Article 10 or change its terms, then the process by which that amendment is adopted becomes self-defeating. The legitimacy of any amendment relies on the rules in force at the time of its adoption. So if the very procedure that enabled the amendment is subsequently nullified, it raises a profound question. Was the amendment valid if it undermined its own foundation? Some theorists have attempted to resolve this paradox by drawing a distinction between different levels of rules. They suggest that certain core principles of a system must remain immutable, while other rules, particularly those governing routine procedures, may be amended. In this layered view, the amendment process is itself protected by being categorized as a fundamental rule that cannot be self-amended. However, if a system is truly self-amendable in every respect, then such a hierarchical separation is not available, and the paradox reemerges. The challenge, then, is to design a framework that permits evolution and adaptation without allowing for the kind of self-undermining change that leads to inconsistency. Another way to address the paradox is to distinguish between the act of amendment and the enduring effect of an amendment. One might argue that when an amendment is made, it is valid if it follows the procedure that was in place at the time of its adoption, even if that procedure is later altered. In this view, the historical legitimacy of an amendment is maintained by the fact that it was adopted according to a process that was then binding, regardless of subsequent changes. Yet this solution only pushes the problem back a step. If the system's rules are subject to continuous change, there is no permanent benchmark to which we can refer, and over time the cumulative effect of amendments may lead to a system whose overall coherence is in doubt. The paradox of self-amendment has important implications beyond abstract logic. It poses a real challenge for constitutional design and legal theory. In democratic societies, the ability to amend a constitution is seen as vital for ensuring that the document remains relevant over time. Yet if a constitution can be amended without limit, there is a risk that its fundamental principles, those that guarantee stability, protect rights, or provide the basis for governance, might be undermined by changes made for transient political reasons. Some constitutional theorists therefore advocate for an amendment process that includes safeguards such as supermajority requirements or separate protected clauses that cannot be altered. Such measures aim to preserve a core set of values even as other parts of the system evolve. The tension inherent in self-amendment thus reflects a broader conflict between the need for flexibility and the necessity of stability in any enduring system of rules. At a deeper level, the paradox also resonates with questions in meta-theory and the philosophy of language about self-reference and circularity. Similar to how the liar paradox challenges our conception of truth when a sentence refers to itself, the paradox of self-amendment forces us to confront the limits of a system that is capable of altering its own governing rules. It raises the issue of whether any system can be both complete and self-referential without descending into inconsistency, a question that echoes themes found in Gödel's incompleteness theorems, which show that no sufficiently powerful formal system can prove its own consistency. Philosophers have debated whether the paradox signals a genuine problem with the idea of self-amendment, or whether it merely highlights the need for a more refined conceptual framework. Some suggest that our traditional understanding of rules as fixed and absolute may need to be revised in favor of a more dynamic conception, one in which rules are seen as evolving guidelines rather than rigid. In such a view, the process of amendment is not a threat to the system's coherence, but an integral aspect of its self-improvement, a kind of meta-rule that governs change while ensuring that the system remains functionally intact. However, achieving this balance is no simple matter, and the paradox continues to provoke intense discussion and analysis. The practical implications of the paradox extend to how institutions design their governance structures. Whether in legal systems, corporate bylaws, or even computer protocols, the challenge is to build mechanisms that allow for change without undermining the very procedures that authorize change. If a system can alter its own amendment procedures arbitrarily, then the long-term reliability and predictability of that system come into question. This dilemma is not merely theoretical. It affects real-world decisions about how to craft documents and protocols that must endure over time while remaining adaptable to new circumstances. In summary, the paradox of self-amendment compels us to grapple with the fundamental tension between flexibility and consistency in self-governing systems. It illustrates how a system that allows itself to be changed can, in principle, change the rules by which changes are made, leading to potential instability and contradiction. Philosophical responses to the paradox have ranged from advocating for immutable core rules to proposing models of defeasible, context-sensitive belief systems that do not demand strict deductive closure. The ongoing debate underscores the complexity of designing systems that are both adaptable and robust, a challenge that is central not only to epistemology and meta-theory, but also to the practical governance of societies and organizations. As we reflect on the paradox of self-amendment, we are reminded that the search for a perfectly rational and self-sustaining system is fraught with deep, self-referential difficulties that continue to inspire inquiry and debate across diverse fields, from constitutional law to formal logic, ultimately enriching our understanding of what it means for a system to govern itself.